Large language models can churn out paragraphs, but without the right retrieval infrastructure, they're just guessing. That's where Retrieval Augmented Generation, aka RAG, comes in. It's the missing piece that lets AI dive into real data, then generate answers grounded in actual facts, or, the ones that you want. This segment is part of my full-blown RAG course, a massive curriculum that starts with RAG basics, breezes through unstructured data, and unpacks advanced topics like knowledge graphs, agentic RAG, and even AI agents. Right here, we are laser focusing on how to fuse retrieval with generative models to build unstoppable AI. Whether you're wrangling text data, searching massive corpora, or hooking up Hugging Face and OpenAI, you'll see how to assemble RAG systems that blow standard chatbots out of the water. Buckle up, grab the course materials that you can find in the description, pinned to the comment, or, even here. And let's turn your AI from guesswork into knowledge. Welcome back. We're now diving into this very exciting section of the course, which is when we integrate retrieval and generation, which is our RAG systems. This is where the magic happens. Our main goal is to understand and implement the Retrieval Augmented Generation, or RAG, architecture. But why is this important? Well, traditional models can sometimes struggle with accuracy and relevance because they rely solely on their training data. On the other hand, retrieval models can fetch relevant information but aren't great at generating coherent and contextually appropriate text. By combining these two approaches, RAG architecture gives us the best of both worlds. It's like having a supercharged AI assistant at your disposal. By the end of this section, you'll be able to do some pretty impressive stuff, like build a RAG model. You'll create a model that retrieves relevant documents and generates high-quality responses. You'll improve the response accuracy, enhance the accuracy of your model's responses by leveraging documents. You'll ensure that the model's responses are not just accurate, but they are contextually relevant, and then you'll learn to optimize the performance of your model, tweaking and optimizing it. I think I've got a fun and interactive learning journey ahead of us. We'll be mixing theory with lots of practical coding sessions. And don't worry, if you get stuck, I've got plenty of resources to support and help you out. Now, here's a quick preview of what is coming up. Introduction to RAG architecture. Start with the basics of what RAG is and how it works. Implementing retrieval systems. How to set it up and use a retriever to fetch relevant documents. Building the generative model. Create a model that can generate text based on retrieved documents. So basically, we start with the theory, then we go back a couple of sections to retrieval systems. We go and we then go back one section to the generative model. And now we integrate both components. So we combine the retrieval and generation, and then we add the optimization and the testing. So we fine-tune the model for better performance. Are you ready? Let's get started. Welcome back. We're now going to explore the RAG architecture. The model combines the strength of information retrieval and text generation to provide more accurate and contextually relevant responses. RAG stands for Retrieval Augmented Generation, and it is a hybrid model that enhances text generation capabilities by incorporating retrieved information from a large corpus of documents. This approach helps in generating more informed and accurate responses. In essence, there are three main components in a RAG architecture: input query, the retriever, and the generator. Let's dive into each of these components. The process begins with an input query, which is the user's input or question. This query is the starting point for retrieving relevant information and generating a response. The retriever plays a crucial role here. So it searches through a large corpus of documents to find relevant passages of information based on the input query. The retriever uses techniques like vector similarity search or traditional keyword-based search to identify the most relevant documents. The retrieved documents are the set of documents or passages that the retriever identifies as relevant to the input query. These documents contain the information that will be used by the generator to craft a response. The generator takes the input query and the retrieved documents to produce a coherent and contextually relevant response. The generator uses advanced language models to generate text that answers the user's query, leveraging the information from the documents. Finally, the output response is the generated text or answer provided to the user. This response is a product of the combined efforts of the retriever and the generator, ensuring that the answer is both accurate and relevant. Now, let's recap the key ideas of the RAG architecture. We started with the input query, which initiates the process. The retriever fetches relevant documents based on this query. The generator then uses these documents to produce a coherent and relevant response. Finally, the output response combines retrieved information and generated content to provide an accurate and useful answer. The RAG architecture offers several advantages. The first is accuracy. By leveraging external documents, the model can provide more accurate and informed responses. This means that the information provided by the model is not just generated from limited training data, but is enriched with the information from the documents provided. Another significant advantage of RAG architecture is relevance. Combining retrieval and generation ensures that responses are appropriate. This means that generated responses are not only accurate, but also relevant to the context of the query, which improves the user experience. Finally, the RAG architecture excels in scalability. The retriever can handle large corpora, making it scalable for various applications. This capability allows the model to efficiently manage and process vast amounts of information, making it suitable for diverse and extensive datasets. Now, imagine a user asks, what are the benefits of a plant-based diet? The query initiates the process in the RAG architecture. The RAG model then searches for relevant documents discussing plant-based diets. The retriever identifies and selects the most relevant passages from a large set of documents. Using the retrieve information, the generator creates a comprehensive response. The output response combines accurate information from the documents to answer the user's query. In conclusion, RAG architecture is a powerful model that combines the strength of retrieval and generation to provide accurate, relevant, and contextually appropriate responses. It leverages a large corpora of documents to enhance the quality of generated text, making it suitable for a wide range of applications. Thank you for your attention. I would just like to add one last thing, right? So this is the most basic RAG architecture. And my goal is that we start here, and this is the focus of this section, and we build on this throughout this course. So hope you're excited. I am. I'll see you in the next video. Welcome back. Let's do this introduction to RAG. You'll find an also called Introduction to RAG folder inside the main RAG. So you go there, Introduction to RAG, and here we go. Okay, a bit too slow. Let me do a copy of this starter file, but you'll definitely find the starter file there. And the goal of the starter file is actually just to have like a bit of data there that we can actually retrieve and play around with. So this is a sample data. It has 30 facts about Berlin, give or take. And for this video, we are going to focus on the setup. The first thing, let's get our Hugging Face token here. And here we go. And HF token. And then we store it under Hugging Face key. Okay, so HF key equals to, and here you go. So we start there. We set it, so we import OS here. And then we are going to set it. So os.environment Hugging Face Hub API token equals the Hugging Face key. And we continue. Now we install a few libraries here. Here we go. So pip install, so LangChain, and then Hugging Face, sentence transformers, and then as well we are going to install this LangChain underscore community and this FAISS CPU. And we add a queue, so we do it quietly with not a lot of verbosity. Here we go. The last piece is to then to import the libraries. Here we go. And let's see. Okay, so from LangChain dot docstore dot document, I'm going to import the document. From LangChain dot embeddings, and I'm not going to import this, so this is out. And then from LangChain dot vector stores dot FAISS, import FAISS. Then from LangChain, and then underscore Hugging Face, Hugging Face, and here I'm going to import the Hugging Face embeddings. Okay, this is also not what I want. And then okay, so I import Hugging Face embeddings. I'm going to import chat Hugging Face, and then the Hugging Face endpoint. Here we go. Okay, we're almost there. And then from LangChain, and then underscore core dot messages import. Let's see if we get, okay, we're going to import the, not to the parentheses, human message, and then the system message, and then from IPython dot display, import display and mark down. So Control Enter, here we go. And that is it. So this is a setup. And let's just, recover, or let's recap here. So display and markdown, this is to show the output in a nicer way. The system message and the human message, these serve so that we structure the inputs for our LLM. The Hugging Face and the chat Hugging Face, these connect to setting up the LLM for the generation. The Hugging Face embeddings, I know that we have not covered embeddings, but we slowly will. But embeddings are numerical representations of our data. So we store our data, which is this, in with embeddings. So we create embeddings out of the data. And then we have FAISS. So FAISS is a database. We store the data, that is our embeddings, in our FAISS, and then document is for structuring the documents. If you look at it differently, with the exception of this, which is a bit, okay, let me actually change so that this tells an actual story out of this. So we are going to set up these documents that we're going to create some embeddings that we're going to store in FAISS. And then we're going to create prompts that will be a mix of a system message and a human message. And then using an LLM from the Hugging Face, so the chat and the endpoint, we are going to generate based on our initial data. So we're going to retrieve, generate an answer, and then we're going to display it with Markdown. So the library sort of tell a story here as well. This is it, and I'll see you in the next video. Welcome back. In this video, we are going to discuss embeddings. And this is something that we'll cover throughout the course, and I'm sure that I say this quite often. I don't want to overwhelm, and I want to ease all the theoretical topics step by step. But embeddings are, important quote, and they are numerical representations of our data. And what we do is that when we're trying to retrieve, we're going to get our query. We're going to create embeddings out of our query, which are mathematical representations. And then we're going to see, okay, we have the query, which has a numerical representation, and what is most similar to our data embeddings. Then we're going to retrieve the top n. So let's do it. Fortunately for us, this is crazy simple. Let's kick it off. We have our data, and I think I said 61, or I said 30, but it's actually 61 facts. So we can actually check. So check how many documents we have. And here we go. So we print with an F string. We have this number of documents. And what we do is that, okay, let's actually structure them together. And the way that we do it is that we apply this document here, and then page content equals text. Here we go. For text in documents, right? So each document here, or basically each element of the list, or each sentence, I think, they will represent one page. And let me do Control Enter here. So here we go. And we need to remove this, but basically this will be for the first 5. We would have, okay, the metadata, page content is this. And let me actually get rid of this, and we are basically doing all of this for all of the documents. We store it under docs equals to this. Let me add here as a comment here, wrap each string in a document, capital D, to represent also the function. Then we have here the documents. We use a transformer-based embedding model. There's many embedding models. We're going to use an open source for now from Hugging Face. OpenAI has them as well, but this one is a fairly good and common one. Embedding model. Here we go. So embedding, and by the way, this part here is just to actually get the model. Embedding model equals, we use Hugging Face embeddings. And then we have that our model name is the sentence transformers. This is the one that we are going to pick. And then the way that this works, so let me do Shift Enter here. This is going to now to get the actual model. But after we create a FAISS vector store for the docs. And our FAISS store is FAISS, and we actually get this from documents. We include the documents and we use this embedding model. And what is going to happen? And we're going to unwrap this. What is going to happen is that this embedding model is going to create embeddings from the documents, and then we are going to store them. This is what is going to happen. And here we go. And so wait, did I run this? I ran, let me run. And now let's unwrap this. So one thing that we can do is, so if we go to our, can add the comments later. So FAISS store dot index. So this is how we start to retrieve them. And then if we go to the index, there's many things here that we can do. And for instance, let's say that we want to get how many. So n, or let me store this. So this is easier. Indexes. So index here. And then we can get, so index dot n total. This is going to tell us how many. 61. Why 61? Because we have 61 documents. So one for each. There you go. So this is something to, so print total number of indexes. There you go. We would print like this. Here we go. What else can I show? How many dimensions? What is happening is that our embedding is attributing a numerical representation to the tokens inside of our data. Let me give it a go. So we have here print total number of indexes, print total number of dimensions. There you go. We would, print total number of dimensions is the index D. So we have 384. This means that each of these documents here has now 384 dimensions, and each dimension has a numerical value that is an embedding. And if we want to have a look, so print the embeddings for vector, for the first vector. There we go. Okay, print with an F string. Here we go. Embeddings for the first vector. Let me give it a line here. Here we go. So each, or better yet, so our first document has this numerical representation. You can see that the values are very, very tiny at some points. For instance, elevated to the power of -5. But in the end, what is going to happen is that we are going to do this, or we have done. So each of the documents has 384 dimensions. And then when we query, we are going to also apply to our query, and it's also going to have 384 dimensions. And then we're going to compare these 384 dimensions of the query with the 384 dimensions of all of our documents, and we're going to see which ones are the most comparable. And that is it. I think there's some intuition here. I think the mathematical part, like 384 dimensions, like what the hell is that? But the intuition is there, right? We create a numerical representation for the data. We create a representation of the query, and then they are comparable. And then we see which ones are most similar. And that is it. So we have the embeddings here. Then we actually come here and we're going to retrieve some documents. I'll see you in the next video. Welcome back. Let me now share with you FAISS, which is a very, very powerful tool that will help us with our retrieval systems by making them fast and efficient. So what is FAISS? First, Facebook AI Similarity Search is a library developed by Facebook AI Research to efficiently search for similarities between high-dimensional vectors. In simpler terms, it helps you find the closest matches to a given item from a large dataset, and it does it really quickly. Think of it like a super smart librarian who knows exactly where every book is and can find related ones in a snap. So why should we use FAISS in our retrieval systems? Here are 3 reasons. First, speed. So it's definitely designed for high speed, making it possible to search through millions of vectors in milliseconds. Scalability handles large data sets effortlessly, making it perfect for applications with vast amounts of data. And flexibility supports various types of indexes and search algorithms, giving you the flexibility to choose the best one for your needs. So how does it work in the end? It indexes your data into structures that are optimized for quick similarity searches. Here's a quick breakdown. Indexing. Convert your data into high-dimensional vectors and store them in an index. Then we have the searching. So when the query comes in, converts it to a vector and searches for the nearest neighbors in the index. And then, returning the results, retrieves the most similar items from the index based on your query vector. Now, important thing is the types of FAISS indexes. This is part of the flexibility that it offers. First one is a flat index. So this is a simple brute force method that checks all vectors. This is best for small data sets. We have the inverted file, IVF, divides the data into clusters for faster searches. This is ideal for larger data sets. And then we have the hierarchical navigable small world. Uses a graph-based approach for very fast searches. This is great for real-time applications. Now let's go and have a look at an example. So imagine you have a large collection of news articles and you want to find articles similar to a given one. With FAISS, you can quickly index all your articles and then retrieve the most similar ones based on the content. This makes it incredibly useful for applications like recommendation systems, document clustering, and more. In conclusion, FAISS, or Facebook AI Similarity Search, is a very powerful tool for efficient similarity searches on high-dimensional vectors. It excels in handling large datasets quickly and accurately, making it ideal for applications like recommendation systems and document clustering. The workflow includes data preparation, index creation, query processing, similarity search, and result retrieval. Data is converted into high-dimensional vectors, indexed using FAISS, and then queried to find the most similar vectors. This process ensures fast and accurate search results. FAISS dramatically improves retrieval system efficiency by leveraging high-dimensional vectors. It enables lightning-fast retrieval times and handles small, massive, real-time datasets with ease. This is it. Now let's see how to apply it, and I'll see you in the next video. Welcome back. Now that we have stored this, we can actually retrieve things. And I'm going to have here our retrieval system. And one question that you might have is that when we're looking at the beginning of the course for retrieval systems, we didn't store anything. And now we're doing it. So why are we adding this over complexity? Which is, a fair question. The thing is that when we're doing it at the beginning, and because we're starting out, we don't really have a lot of data. So as we do anything, it just gets stored in the CPU, which is okay, is enough. But when you think about a massive number of documents and data and video and PDFs and EPUBs, right, we can not have this, pre-processing each time or each day that we use it. We want to store it. So for instance, if you take the example of the course assistant that hopefully you're using it, everything is stored in a database already. So you just retrieve from the database because everything is prepared. So what happens is that what you do, so the usage starts now. So there's this pre-prepared thing that I built, and now you would retrieve from it. And hopefully this made it clear. The way that we do it, so you retrieve relevant documents. What you do is this FAISS _ store. So you go to it, and there is this similarity search. And inside this similarity search, you need to include two things, a query and a K. What is this query and K? So the query is the actual query of the user, which for us would be, let's say, what is Berlin known for, right? So this would be the query. And then a K is how many we want. So how many documents? Let me do Control Enter. So we do this. And what we get as an output is that we get the documents that are most similar. And in case that you want, we're not going to use it, you can do it similarity search with score. This is also a possibility. You actually get the score here. And in case that, you add more, let's say 10, here you go. So what is happening is that we are getting the documents that are most similar. And you could ask, okay, wait, why is the value increasing? Is that this score is a distance. And what we're trying to minimize is distance. So when we're looking at something that across a vector space that is most similar, what you minimize is distance. And therefore, we actually look for something that has the least value. And hence why we have it as a score. Here we go. We would do here docs or retrieved docs. And it would be the FAISS store similarity search. So this is how we would do it. Now, it's a very good practice to actually build a function for retrieving documents. Here you go. So define get relevant documents, and then we return FAISS score similarity search, and we include the query and the K. And that is it. Now let's talk about generation. I'll see you then. Welcome back. Let's now do the generation system. Here we go. So, generative system. And we start here. So load the LLM. So LLM equals, use the Hugging Face endpoint. Here we go. Parentheses. And then repo ID equals 2. And it is the Microsoft soft. Here we go. Slash fee with capital P hyphen 3.5 hyphen mini hyphen instruct. Here we go. And then set the task text generation or generation text. Generated text, I think. But text generation definitely works. And then we get here our chat model. And here, so chat model equals to our chat Hugging Face LLM. Here we go. And we have it here at this point. So our LLM is loaded. Then we start by building the messages. And here we now define the system and human messages. Here we go. Messages equals to, okay, not this. And we start here with the system message and parentheses. Okay, let me add this. You are, okay. So our data is about Germany, and let's say trivia or, fun facts. Well, nothing in Germany is fun, but I would say here, you are a tour guide with a thick German accent. By the way, I have a fantastic Arnold Schwarzenegger accent that I'm not going to show you. Well, maybe one day. What you are a tour guide with a thick German accent. Yeah. What is good outside of Berlin? Plot twist, as a proper person from Berlin, the answer is nothing. But this is a question that you may include here. And then we have the messages. We then have the AI output here. We have the chat model, but okay, let me actually try this, but I don't think this is going to work. Here we go. It's a deprecation warning. We need to use .invoke. This is the method that you need to include to make sure that we're doing it, the correct way. And it's a deprecation warning so far, but one day it will for sure become not deprecated. And then it raises an actual error. And therefore, we would then display in Markdown the AI output.content. Okay, let me fix this. Markdown. Okay, let me try it now. Incomplete. Aha, I'm missing a parenthesis. Let's try again. Schönen Tag, mein Freund. Okay. Well, okay, this is completely in German. You are an English tour guide with a thick German accent. Let's try again. And alrighty, still thinking. So this is, let's say, the initial generation system. And then what I'm going to do, okay. Well, we're still doing German. You are an English tour guide with a German accent. You reply in English. Let me try again. And what I want to do to wrap up this video is that I want to build a function out of this. This is the ask, so the generation. Okay. You reply in English. What is good outside of Berlin? Your task is to reply in English. Okay, let's try again. Okay, but not because now it's personal, it's not doing what I'm asking it to do. At the same time, let me actually then start building the function. I'm going to define, I'm going to call it Generative system. And inside, I've actually not finished this, but there's going to be two things. There's going to be the context, and there's going to be the query. So context and query. Here we go. And at the same time, what is happening here is that we are unsure, or basically, there's nothing here currently that is indicating that we're using our data. This is just a general question. And therefore, what we do here is that we come to the human message and we add, let me actually put it as a comment. What is good outside of Berlin? And then, or better yet, let me do it differently here so that it's, crystal clear query. What is good outside of Berlin? And here we go. And then we would add here, answer the query based on the context. And then the context here is, of course, coming from above, which we have not defined. But I'm actually going to leave that in the next video. So I know that I'm not finished, but I was actually, starting building the RAG system, and that's not actually, the purpose of this. That's the purpose of the next video. I'll see you then. Welcome back. In the last video, we did our generation system, and at some point, I actually started building the RAG, which was a side and not the purpose. So I'm going to take a step back, and this is going to be our generative system for now. And here you go. That basically we generate something based on a query. Here we go. And we start here. I'm going to give it a tab, and then we are going to return. There you go. So display output, display markdown AI output dot content. And here we go. So this is the function. Then, how can we add here the RAG system? The RAG system is combining the retrieval and generative system. Here we go. How can we add it here? So we're going to define this RAG that as an input has just one query. And then what is happening is that we need to first call this, so get relevant documents. Here we go. We start with the context equals to get relevant documents based on a query. And let me actually, so define, let's say that we add this k equals to 5, and this makes it so that if I don't specify it, the k is always equal to 5. Therefore, query, k equals to 5, but we can leave it out. Then, I also want an output here, right? So how can we actually do it? So we have the query, and then we return the generative system, and it's already adding. This must have a query and a context. And the context here is that we answer the query based on the context. And this context is then also added here. It's very important. Like all of our LLMs, they're very good, but you do need to be very specific here. So one pro tip that I am to give you here is that always add this sentence. Only answer with information from context. And then we add here an F string. Let me actually add 3 quotes. And then we have a deeper system message. Here we go. Only answer with information from context. And then if you don't, wait, I need to take out this. If you don't have information, say you don't know. Always add these 2. I found that it does wonders for the quality of our outputs. Because you see, our LLMs are designed to give us an answer. And unfortunately, saying not knowing is not a straightforward or standard thing. And even if it's sometimes they do, like add these 2 sentences. Only answer information from context. If you don't have information, say you don't know. This is a pro tip from me. So I've also changed here the system. I have now built the RAG system here, which is a very simple one. And then we can, test the RAG. So let's say that we have here a query equals to what happens in God forbid Munich. You go, and then we apply the RAG based on our query. And then let's get an output here. Based on the provided documents, there is information about Berlin's blah blah blah. However, there's no specific information about what happens in Munich from these documents. And it's exactly what we wanted. Let's give it a few tests. So prepare test queries. Here we go. So query list equals to, oopsie, with the square brackets. And okay, so let's say, where is the German parliament? So comma, and then where is Portugal, or where is Portugal? Let's do something like we invented the pastel de nata, which is a very famous Portuguese dessert and pastry. And yeah, let's just do these two. Can add more and more, but basically what I want is a proper answer for the first one and non-answer for the second. And then we actually, test the RAG system for query in query list. Then we have here the RAG. There you go. Yeah, the first one. And it's also cool that it's actually cool that it showed. It's cool that we often have this source. It becomes, it's very cool. And then it talks about the Reichstag, which is the parliament in Germany. And then on the second question about the pastel nata, then we have no information, which is exactly how it is supposed to be. It's a bit wordy. Based on the document, there's no specific information. There's information, therefore they don't have information. It's a bit too verbose. You can also add that to the system message. Don't be verbose. But a good answer is still a good answer. And that is it. This is like the simplest way that we can actually build a RAG system. It didn't take long. It led us to actually explore a bit the database, which was a key element that I wanted to bring. And if there's like two things that I would highlight is the database using FAISS as a very easy way to store our data, where we store the embeddings and then the system message. Add these two sentences, and I think your RAG systems will just improve all the time. I'll see you in the next video. Welcome back. We have been talking about text generation, and now I want to show you something which I find quite cool. For this specifically, even though it's considered legacy, but I'm going to talk about it later, you do need to have an API key. Now I cover this API key, I think in the next section, when we cover the OpenAI models. For this one, we're using GPT-2 because I didn't want that you focus so much on API keys. But for this one, I want to show you something. Now, you don't need to do anything with this. This is just, me showing off. Now, the way that the text generation works is that it always gives some kind of, probability to tokens. And for instance, if I were to write here something, and then what this does is that it completes with something else. Let me show it to you. So for instance, you are a player of rock, paper, scissors. Your strategy is to play randomly. Pick your move. No, I'm very specific here. You are a player of rock, paper, scissors. Your strategy is to play randomly, pick your move, and then submit. And okay, this is actually not at all what I wanted. Let me change this. So what is happening is that it's giving me code. Pick your move. And okay, so let me try again. Pick your move and don't use Python. So let me try again. Submit. I choose rock. And this is what I wanted to get at. Now, if I say play randomly, you would assume that there is a 33% chance, but it is not. Now, let me come here. So I want to show probabilities, full spectrum. Let me try again. Let me submit. I will pick rock. And we see here that currently rock has 19% and paper as well, and scissors 7%. But this is based on this current way of tokens. So if I were to add now, so let me come back here, choose either rock, paper, or scissors. Here we go. Try again. Rock. So rock here now has 46%. Again, there's nothing random about this strategy. And then you have rock, paper, and like scissors doesn't even pop. The thing is that because the way that these models work, the way that they are trained is on actual people, people choose rock most of the times. Not paper, definitely not scissors. And I have played around this also as a background story. A few months ago, I attended a talk by one of the senior software engineers that work with Gemini from Google. And the whole talk was how difficult it is to have an LLM like Gemini, and as you can see also one of the OpenAIs, to play rock, paper, scissors. Because they choose rock all the time. Because that's how they were trained. People choose rock, they choose rock. Therefore, this is how you can beat rock, paper, scissors. Also in real life, never choose rock. This is, I think, a good strategy, especially at the start. Now, this works for a lot of things. So, for instance, let's try as well. Roll the dice. Let me come here. You rolled a 6. But you see here, 6 has 27.5%. And so this is a dice, right? Each of them randomly would have 16%, more or less. But you can see that 4 and 6 and 5, they all have above 16%. And for instance, 2 and 1, they are apparently not considered random throws of the dice. So this is also important to have in mind. And roll the dice, I get it, right? The dice can have more than 6 sides. It can be one of those dice that can have multiple. So you have this, but it's very cool to see like even 7 has a higher probability than 1. Like, how weird is that? And it's always like what people think. And if people think some way, the model is trained in that way. And this is how we get the output. We may think it's random, but it's not. Like, it's really based on what you pick. And this is our goal for this basics of generation models. And we're going to build and try to really fine tune this GPT-2. And currently we're using here, this is legacy, right? So this is no longer updated. GPT 3.5 Turbo Instruct. So this was the last one to be added here. You can also play around with this. I like it. I think it's cool. I think it's very cool that we see how this works. There's always the classic. Let me give you another one. How many R's are in strawberry? This is a classic. Let me click on submit. There are 2 R's in strawberry. So 2. That's a 48%. And 3 gets 10. Let me actually then... Ooh, that's actually a good one. Let me show you the tokenizer once more. Let's see here. Strawberry. 2 tokens. 3 tokens. ST raw berry. And this is where this is coming from. Because if you look here at the playground, so there are 2 R's in strawberry. This is coming because it's just counting this last 2 in this token. And let me see if it matters based on the model. No, it's always 3 tokens. So this is how, and this is, but it's different. So STR, raw berry. So this is the 3.5. But it will also happen in the 4.0. So this is the reasons. Actually, I think this blew up a bit in my LinkedIn. that ChatGPT cannot count how many R's in strawberries. And if you actually play around with it and ask why, then it will eventually come to the conclusion that yes, it has 3, and the tokenization was really the issue. Bottom line, this is all based on probabilities and getting the token that has the highest probability, but not necessarily the highest, as we saw. It will be one of those. There are some parameters here that I'll show you later on that deal with the randomness. Another way to put it, it deals with the creativity of the model that you get to play around. If you have any questions on this, let me know. If you find any cool things that you'd like to share with me, please do, because I don't know, I'm very geeky about these topics. But otherwise, I'll see you in the next video. Welcome to this section on RAG with OpenAI API. Now imagine that you're flipping through a cookbook, pages filled with delicious recipes, cooking tips, and secret ingredients. Now, what if I told you that by the end of this section, you could build an AI that not only finds the perfect recipe from that book, but can also walk you through the cooking process, suggest alternatives, and answer any culinary question you throw at it. That's the kind of power we're about to put in your hands. In this section, I'm going beyond the basics and diving into the future of AI with RAG using OpenAI. Now, this isn't just another section, right? This is where everything comes together again, but now building something cutting edge. So beyond the basics, now everything from now on is cutting edge. And I truly think that this section is great. It is the game changer that you have been waiting for. Here, you won't just learn how to use RAG, you'll build a fully functional system that combines the best of both worlds, the retrieval and the generation. So I'm no longer talking about everything that we have done so far. Now we'll be working with real data and building systems that can handle really complex tasks, handle a lot of data at once. And by the time that we're done, you'll be able to take any collection of data, whether it's a cookbook, research archive, customer queries, and transform it into a smart conversational assistant that can retrieve and generate information with ease. This is where you turn knowledge into actions. What will we learn? So here's what you're going to master by the end of this section. We'll start with data conversation mastery. You'll learn how to take raw and structured data like PDFs and images and transform it into AI-ready formats. This is the first critical step in making data usable for advanced AI models. Additionally, we will use GPT for OCR. What is OCR? This is the technology that reads PDFs. You'll dive into using these GPT models not just to recognize text, but to understand and extract detailed, structured information. It's like, OCR on steroids, but it's going to change how you approach data extraction. We'll be building RAG with tools like FAISS and OpenAI's embeddings. We are going to create a system that can search through vast amounts of data and pull out exactly what you need in an instance. And then we'll seamlessly integrate our RAG. So this is where the magic happens. You learn how to build a RAG system that doesn't just find information, but delivers it in a human-like conversational format. And then lastly, you'll be fine-tuning with prompt engineering. You'll refine and optimize how your AI understands and responds to queries, making sure the output is accurate, relevant, and useful. And by the end of this section, you'll be able to convert and prepare complex data. So whether it's images, PDFs, you'll be ready and you'll know how to prepare it for AI processing. We're going to extract rich, structured information, so move beyond basic OCR and start pulling detailed, meaningful data, and then create and utilize embeddings, so represent your data in ways that can make it easy for AI models to retrieve and compare. We're going to build a powerful retrieval system, So we're going to develop it so that it's not just fast and efficient, but it's also tailored to your needs. And then we're going to integrate it into our RAG, so develop the systems that combine both of these worlds. And then we'll optimize our AI inputs and outputs with precision, with prompt engineering and fine tuning. Therefore, by the end of this section, you'll evolve from a learner into a creator. And you'll build these very cool and advanced AI systems. This is it. Let's get started. Now that we have set the stage for what you will achieve in this section, let's get specific. Let me talk to you about the case study, so what we will solve with this practical application of RAG and OpenAI. We'll be diving into the world of cooking books, which is a treasure trove of recipes, techniques, and culinary wisdom. But why cooking books, right? Isn't this like a stupid example? No. They're really like the perfect example of unstructured data that people regularly interact with. These books contain a wealth of information, but it's not always easy to find what you need when you need it. You might have a dozen of recipes for bread, but which one is the best for beginners, or the ingredients that you have? Or you might know the ingredients for a cake, but what if you need to swap out an item because of a dietary restriction? These are the kind of challenges that a well-built RAG system can solve quickly, accurately, and contextually. Let's have a look at the process. In this case study, we're going to start with a typical cookbook in PDF format. Each page is filled with rich content, recipes, tips, and sometimes even photos. And your task is to convert these pages into a format that our AI can work with. We will begin by converting the PDF pages into images. Now, this might seem straightforward, but it's a very critical first step in making the data usable. Why? Because once the images are prepared, we'll move on to using OpenAI's GPT models to extract the text. So our GPT models can read images very well, PDFs not so much. So it's part of the challenge for them. This is why we do this step of transforming into images. But we're not just interested in raw text. Before I get to it, we really want the data structured, right? So we need to work with our GPT model to take the data from the pages and then structure it in a way that we would then want to retrieve it, right? So think about titles, ingredients, maybe tags. Like the way that you'd search for stuff is the way that we need to structure it. Then we'll be focusing on filtering and embedding the data. So as you extract this information, you'll also be filtering out the noise. So discarding irrelevant context so that your final data set is clean, focused, and ready for the next stage. And once we have refined this data, we'll create embeddings, which are essentially numerical representations of the data. And these embeddings will allow our system to understand the context and relevance of each piece of information, making it possible to retrieve the right data at the right time. And then we'll integrate everything. So what makes this case study truly powerful is really, our RAG system. You won't just build a system that can find a recipe. You'll build one that can respond to questions like, how do I make a gluten-free version of this cake? Or what's a good side dish for this main course? Or, some questions like, give me a recipe that will impress my friends. Like, stuff that you would think, or at least that I would think. And therefore, your AI will be able to pull in the relevant information and generate a response that's useful and context aware. So you also see me talk a lot about context. Context is very, very important, right? So it's not just being literal. Context matters. And therefore, I'll share with you a lot of cookbooks. We'll use one because the sake or the purpose is to show you how one works. but there's a lot for you to play around, so I've shared more. And therefore, as we move through this case study, I want you to keep in mind the bigger picture, right? So we're using cooking books as our example, but the techniques and tools you're learning can be applied to almost any domain. Think about how you can use these skills to transform other types of unstructured data, so research paper, legal documents, customer reviews, into dynamic, responsive systems. Conclusion: we want to build something useful. So this is our chance to build something that's not just technically impressive. We have done technically impressive so far, but this for me is genuinely useful. So let's get started and let's see how this works. I'll see you in the next video. Welcome to this first practical video. Please come to the RAG folder and then RAG with OpenAI. We're going to click on New, More, and Google Collaboratory. Before we get to it, I want us to get an OpenAI key. This is something that is a paid service. So you do need to put some money there. So maybe $10, $20. We won't use much, I promise. So let me log in. So I have been using this significantly for the past 1 year, and let me see if I can even share it with you. So my billing, so I've spent in total, I think $20 over 1 year. So definitely not a lot. I have used I have put so much through it, experiments, like my research assistant uses it. It's very, very affordable. And we're going to even make it more affordable because we're not using the most expensive model because we don't really need. So now we need to get an OpenAI key. Let me see. I always confuse how to get it. No, your profile. User API keys, view project APIs, and here we have it, right? So you should try to search for something related to API keys, and then you can create a new one. So let me GenAI key, whatever. Let me put everything in lowercase. And yeah, so here we have it. Then I would then copy this key, click on done. Now, what I want to do is that I want to embed this in my Google Colab so that you don't always need to come here and fetch it. What you can do, this is a very, very cool feature here that we have in Google Colab, is that there's this secrets here on the left. You click on it and then you can add a new secret. I'm going to call it, Gen AI course, something like this. I do Control V so that I include here the value. Here we go. Now I hide it so people don't use it. And I'm going to activate it for this, specific notebook. And this is something that is across all of your notebooks. So this is a very, very cool feature. Let me add this. So RAG with OpenAI. Here we go. And we also need this here as well. Oopsie. Let me copy this code. Control V. And at the same time, I also need to connect to the Google Drive. Here we go. Connect to Google Drive. Lovely. So we have both. Oops, I'm clicking on way too many things. So here, instead of secret name, we change this to this name, which in this case would be Gen AI and then course. Here we go. and not actually this, because then I show it to all of you. OpenAI API key equals to this, and now no one can see it. Then I need to mount the drive. This is also important, so connect to Google Drive. And here you go. Like, I'm a very big fan of all the Google products. Like, I use not all of them because they have too many, but like everything from tasks to notes, I use all of them. So one of the reasons why you see so much of Google stuff here, with the exception of Gemini. That one I don't use that much. Funny, right? So let me click here. So this part here is complete. We have our OpenAI API key. Let me close this. And to highlight, like, we're not going to spend that much money. So maybe $1, $2. I don't even know, but it's definitely not a lot. So be at ease. We're not going to go overboard with this. We're going to have a look at our case study, which is one book. We're going to use a tiny book, but of course I'm sharing with you a lot of books so that you can even have a bigger project. So you can build a better RAG. That is a challenge that I leave at the end to you. But with this, our key is set up. We're now done, and let's go to the next video. Welcome back. So now that our setup is partially done, I need to add here my directory, so %cd, and then I come here to the folder, my drive, GenAI, RAG, and RAG with OpenAI. So copy the path, there you go, and let me do Shift Enter. Now here, what I want to do is that we are going to perform, it's kind of like this OCR. OCR is, I like reading PDF files and so on, and transform to images. So this is our end goal. And what we do first is that we are going to come here and we are going to transform first all of the PDFs into images. This is our initial step. So let me install stuff first. So pip install and PDF to image, and then we're going to do this apt get, and then install. We do this Y here, then popper utils. So this is sort of a requirement for PDF to image. Otherwise it won't work. And it's not popper, but popular. And pip install pi, that's a no. Shift Enter. And the next step is to import the libraries. We can, so from PDF to image, we're going to import convert from path. And then we import OS as well. Here we go, Shift Enter. And we can kick it off. What we need to do at the end, so that you have in mind, so at the end, we want to have, so we need a PDF path. Where are they? PDF path equals to, and it's in our directory. So what we need to do is that we need to include the name of our PDF. And I'm going to use this one. It's a tiny one, so it's 136 pages, but it's enough that we can start to play around a bit. So things mother used to make capital T.pdf, So things mother used to make dot PDF. We need to have an output folder like this one, images. So this is where everything is going to be stored. You can see that I have here already while I was playing around to build it. So it's here, but I'm going to create here a rule that it will work if you have and if you don't have it. And it's also good that we have this image paths. So this is what we want at the end, right? So we want to have all of the images, but we also want to, store them. Therefore, we need to create a function that converts PDFs into PDFs into images and stores the paths. So define PDF to images, and then we are going to include the PDF path and the output folder. Oopsie, output folder. Now over here, we are going to create, so if we don't have the output folder, which in this case, I actually don't know what I'm going to do. So you either may have the images folder or you may not have. Therefore, we need to set up this rule. So if in the operating system, so if not OS path exists, which one? The output folder. What we do is that we make it so OS make a directory output folder. Then we are going to images, so we're going to convert PDF into images, and this is done with images, and we use this convert from path, PDF path. We need to save the images, but I also want to save the image paths. This is important for the future. So as a list, and here save images and paths. What we do is for I image in enumerate the images. So we start, so the image path is what we have. So we need to have the output folder plus the name of the image. And what we do is this OS path join. What we join the output folder. So in this case, images, and then the name of the page. So this is one simple way with an F string page, curly brackets, and then you do I plus 1 and then dot JPEG. So this is part 1. We would then save, so image dot save, yes, image path and JPEG, and then the image path we append the image path. So we're always like adding the image paths, and then at the very end we would return the image paths. So this is something that we want to store. So let me click here on Shift Enter, and therefore we can then use PDF to images, PDF, and then to images, PDF path, and the output folder. Let me actually delete this so that you see it being created. And so Shift Enter and then Control Enter. Let me update this here. And I'm always like, this is like the moment where it's supposed to happen and it has not happened. Okay, now I'm starting to get a little bit worried. Okay. So my function here is a bit off, right? So because I have everything, so if not, so let me bring it down. Let me check if it ended up creating something. It did not. So let me do Control Enter again. And let me try again. It's taking longer, which is good. There's something that is different. Let me now update. We see the images. This is very, very good. And so it's still not here, but it's starting. Now, this should not take that long, but it's still fine. Still, I'm going to stop this video here. I think it's working. It's doing a fantastic job. And next video, I'm going to return so that we can continue on this part of now looking at the images, but actually it's now done. Let's see. Okay, here we go. All of them are here. Okay, I was like, this was not that many, but all of them are here. This is very good. It means that our thing worked. Have in mind this part about the indentation. This is always important. We can stop here. I'll see you in the next video. Welcome back. In this video, we are going to use our GPT to extract information from the images. Let's get started. First and foremost, we need to install. So pip install OpenAI. The step number 1. Step number 2 will be that we import libraries. So from OpenAI import OpenAI. Be mindful of the uppercase O, A, and I. And not OpenAI error. And then we import base 64. Why is this important? The images need to be encoded, and therefore we import this base 64 to make it happen. We're going to start by setting up our connection to the OpenAI API. This is step 1. So set up connection to OpenAI API. Client, this is us. We use the OpenAI, and then OpenAI is the OpenAI API key. Let me see. So this was the name that we gave it. And then we also need here to choose the model. Not here necessarily, but I like it. So GPT 4o mini. This is the one that we are going to use most often. You can alternatively just use the GPT 4o. They're both very similar. This one is cheaper. So have that in mind. So let me do Shift Enter here. And now we are going to read and encode one image. So image path equals, we go to our images and now we need to pick one. Now let's not just pick any. So for instance, page 10, which is blank. Let's also not pick one that, is the author's foreword. And let's pick one that has actual recipes. So this one here, we have breads and we have Boston brown bread. So this is something that we can use. So images, and then page 23.jpg. Here we go. And then we open, so with open image path. Here I have RB, but I don't recall what is RB. Let me come here, or let me ask Gemini. What is RB in this code? Here we go. Gemini is thinking, read binary. And so we read binary, the image path, as image file. Here we go. And then the image data. Now we use the base 64 to B64 encode. Let me get rid of Gemini over here. B64 encode, image file, we read it, and then we decode as UTF-8. So this is the format that you need to pick. Now, this is absolutely meaningless. So if I have a look here at our image data, Control Enter, we get an error. Why do we get an error? Images, page 23 without the underscore. Here we go, Control Enter. Here we go, right? So we have this is absolutely meaningless. I mean, to a human language. So we don't care about this, but it's there. And then we are going to call GPT for Omini, but first, it's very good that we define the system prompt, system prompt. Let's keep it simple for now. Equals something like, please, let's always be polite, analyze the content of this image and extract any related recipe information. Here we go. We close this. So this is done for us. And now we call the OpenAI API. And we need to use the chat completion method. Let's kick it off. So response equals to client. So client chat dot completions dot create, and here we kick it off. So model equals to model, and then the focus is really here on the messages. Let's include this as a list, not extra body. So we start here. So provide the system prompt, and then as the dictionary, role system, and then the content here will be our system prompt. System prompt. So this part is complete, comma. Now the user message, right? So this system prompt, initially this is what is in the, let's say, the backend. And now the user message will be what you would, write on ChatGPT. Now the user message contains both the text and image URL / path. So we kick it off with the role. This one will be set to user. And then the content here, we start here with a list. So not extra body. I have no clue what that extra body is. So content. So this is the image from the recipe page. Here we go, comma. Then we start with a dictionary. And if you get this shortcut, take it, because it's one that's very likely that we screw it up, because there's really like a lot of different things. But basically, so we start with the content. So this is the message from the recipe page, type image URL. So this chat completion is aware that we can add image URL. And then here, image URL is a URL, and then we include the data. So image JPEG, base 64, image data. So this is what we added here. And then we also add here to make it, extra complete here, comma. So detail is low. So if we have a look here at our page 23, so level of detail, this is very low. Will also help, guiding the GPT on how it works. And I'm going to have this here. So response is this. Let me do here Shift Enter. So we have now extracted from the API. And now basically we display the content. So response equals to, or, let's go with response equals to, no, something else, because this was called response. So GPT response, let's call it like that. We go to our response. This is actually something that maybe I want to show you how it works first. Let's do it step by step. So this is all of it, right? So we have all of the information. We have prompt tokens, we have total tokens. Prompt tokens is quite high because of the image. This is important for you to know. And we have the chat completion, and what we want is this choices. Because this is where all the information is coming from. So response, let's go to choices. And if I just do this, we get this part. So we are already almost in just, the information. We do index position 0. Here we have one extra level. Then we go here to message, right? So this is the message. Dot message. We have one step further, and now we need to go here to the content. Here we go. So this is something. Doesn't look good, but it's there. So GPT response equals to this. And then, so that we make it extra nice. So from IPython display, not this, import markdown display, and then display markdown GPT response. Let me do Control Enter. And here we have it, right? So we have our breads, we have the ingredients, the instructions, so we have everything. So we managed to extract the information. The question is, what do we think of this information? And how, from a database perspective, should we envision this? So this is part of when you are building a RAG system, we should have this product approach view. And we're not going very deep into it, but I want to add some details. And I want to focus on that in the next video. Until then, have fun. Welcome back. In this video, we are going to try to improve our response using here some prompt engineering. First things first, I want to define a function to get the GPT response and display in Markdown. This is something that we're going to do repeatedly, so might as well define GPT get GPT response, get GPT response, and actually I don't want to include anything here, but basically we would get this, so GPT response equals to this, and I would then, do this, return display Markdown. Okay, let me give it a try as well. So get GPT response, Control Enter, and here we have it, right? So this is going to save a bit of coding. Let me hide here the output. Now, I want us to focus first on this system prompt. And I want us to think what else we could get. So anything that we would like to have here as well. And there's like so many things that we could have when it comes to our, system prompt that we could essentially retrieve. So if we have a look here, so let's start with our system prompt. So we start here. So define improved system prompt. And here you go. So this part is okay. So please analyze. And what I want, so extract any related recipe information. This can be improved. So extract any related recipe information into structured components. And so our goal here is that we have this in a way that's, it's structured. Specifically, extract the recipe title, list of ingredients, step by step instructions. But now, like, really think of it from a database perspective. So we can also extract the cuisine type. We can extract the dish type. But if you think really on how we do searches, right? So search for any relevant tags. And we could potentially even include the tag. So include any of the following tags. That is an option. So any relevant tags or metadata. But this is really part of something that we want to structure this. Because, again, a RAG is how to access a database. So we access the database with an LLM, we get information, and then the LLM is going to reproduce the data in a way that's tangible, in a way that works with a language. Therefore, we also need to help the LLM actually find the information. So we include this, and then we would say, okay, the output must be formatted in a way suited for embedding in a retrieval augmented. And okay, let me zoom out for a bit in a retrieval augmented generation system. And this is going to be our system prompt 2. Shift Enter. Then we come here. Let me do it again. But after this one, we're going to use more copy pasting. So call the API to extract the information. So response equals to, I use the client. Let me zoom in a bit. Dot chat dot completions dot create. Open parenthesis, and we can kick it off. So model equals to model, comma. Messages here equals not extra body, and we can kick it off. So we start with the first dictionary. This is related to the system. Here we go, comma. The content will be our system prompt 2. Here we go. And then we give it, so we talk about the user. So role, and then user, and then the content will be, we start as a list. I really wonder why this extra body keeps on popping up. So this is the image from the recipe page. So this is point 1, comma, and then we can kick it off. Type. Let me also come back down. The type here will be a image URL, comma, and then we focus on the image URL, and here we go. So the URL will be this, and I use the shortcut. So it's an image base 64. The image data is the actual information about the image, detail low. And I also want to add something here. So after this one, let me do temperature equals to 0. So basically, I don't want creativity. So the goal is to extract information. There's no creativity required here. It's a very, very mechanical job that needs to be done. Therefore, temperature 0. Shift Enter. Let's see if we don't get any error. But now we would, print the info from the page with the, improved prompt. Get GPT response. And here we go. So we have the breads, ingredients. We still have everything. So the bannocks, the Boston brown bread. We have step-by-step instructions for bannocks, for Boston brown bread. We have the cuisine type. We have dish type. Then we have relevant tags, metadata. So quick bread, breakfast, comfort food, homemade. And you can keep on exploring this, right? So this is very important that you have a product mindset here. What is the purpose? And this is an easy approach and is something that you can start, but as you iterate, right? So as you improve, then this is something that you would also change, right? So you change the prompts to organize everything in a way that you want your product to be used. But enough of this. I'll see you in the next video. Let's keep with this journey. If you think about it, like we're not even on embeddings, right? We're just focused on data processing, which is the most important or the most difficult part in a RAG system. I'll see you in the next video. Welcome back. In this video, we are now going to extract the info about all of the images / recipes. Here we go. So extracted recipes equals to an empty list. And then what we do is for image path in, so for image path in image paths. And okay, I went way too much, but this was the initial one that we stored here. So all of this that we did initially is now coming to bear fruit. So we open read binary and then image data. We do the same process. So base 64 and then B64 encode. And we would then include the image file dot read, and then we would then decode as UTF-8. So we start here. Don't forget to go to the left because of the indentation. We would call the GPT or the OpenAI API here. So let me start here. So we start by reading and decoding images. We call the OpenAI API. I'm going to copy from above because this was working out for us. We do Control V and tab. This part I no longer need. So model equals model, and then this remains absolutely the same. And then what we do is that we would then extract the content and store it. So GPT response. This is our response choices message content. Extracted recipes we would then append. But not just this, we store it differently. As a dictionary here, we store the image path. Here, this is the image path, comma, and then the recipe info. Here, this is our GPT response. Now let's add some debugging. So print with an F string. So extracted information for image path. Go here, you give it a line, and then you would include the GPT response. Here we go, and you give it another line. Just for the sake of debugging, what you can include, you'd say, okay, so print here with an F string would be processing image, and then you'd give it the image path. Here we go. Let me do Control Enter. We have something that is wrong. Let me triple check. And yes. So I closed here the dictionary, but I should have closed it here. Let's try again. Seems to be working. So processing images, page 1, and then extract information. I can't extract specific recipe information from the image you provided. Let's go to page 1. If you go to page 1, this is just the cover. Do we want to store the cover? Like, it really depends. We may want to store what is the title and so on. But for the sake of, just focusing on the recipes, this we don't need. So this is the right thing to do. This is going to take a few minutes. I'm going to stop here and I'll return in the next one. So what we have done so far is that we have been able to extract all the information from a given book. And yeah, I'll return in the next video. Until then, have fun. Welcome back. Let's kick off this part where we extract the frames from the video. We need to install something, pip install, and it's this movie pi, shift enter, and then load library, here we go, from movie pi dot editor. I import the video file clip, define output folder, so output folder going to be frames, and then so if not os dot path exists, output folder os make directory with the output folder. Here we go. Let's do shift enter, and then we need to load the video. So this is something that is pre-prepared. So video file clip is the video path, and this video path was defined all the way in step 2. So here we go, shift enter, and now we extract the frames. And this is nothing. So we start with, frame path. So this is going to be an empty list. And then we have this interval, right? So why? Because we're not going to extract 1 frame per second. If you have in mind, I think my videos, most of them are 30 frames per second. Even like sometimes when I record this one, for instance, this is 60 frames per second. And therefore, this is quite a lot. And even 1 frame per second is massive, right? So I've been speaking for 10 seconds, the screen has not moved. So there's a lot of information that we don't need. Of course, we may lose some stuff, but that's part of it. This is why we also have the transcript. This transcript is supposed to be there to help. But I'm going to do, at each 10 seconds, I'm going to do 1 frame. So, second 1 frame, and then second 11, another frame. And therefore, this is what is more than enough. So for t in range, we go from 0 all the way to the video duration. So integer video dot duration, and we go at steps of interval, which is 10. Here we go. Sorry. So the interval, so video duration, parenthesis, interval, and then there's a parenthesis too much. We start by getting the frame path, and then os dot path dot join. We have the output folder, and then we have this f string where we're going to call it with a frame of t. So, second 10, 10, so 10, 20, 30, and so on. T, but let's add it with 4 decimal case, so 0010, 0020, and so on. So 0 for D. And then dot PNG, here Here we go. And then we save the frame at the specified time. And then it is video dot save frame. And what happens is that we, of course, have this save path at time t. And then we append everything. So frame paths dot append. This is more for the future, in case that we want to use them immediately. But basically, the saving is here, and then we also have it here in the frame paths. Let me do Shift Enter. And in general, it's very good that we save everything, because it's not that long. Sometimes it takes 1 minute, 2 minutes. I don't know how long this takes. Could take 5 minutes. But it's very important that we have a scalable product, and this is part of it. With this, we're absolutely done. Step 6 will be embedding audio. So this is the next one that we need to do. I'll see you in the next video. We have talked so much about embeddings that I felt, okay, you know what, let's have like a proper video dedicated to it. Because this is how AI models can understand the meaning behind words, sentences, and even entire documents. What happens is that raw text is transformed into a numerical representation that captures the essence of the information in a way that machines can process. Now, this is quite important. It's quite a bit here that we need to understand step by step. What are embeddings? First and foremost, so at its core, embeddings are dense vector representations of text. Think of them as a way to convert words, sentences, and even entire documents into numbers, specifically into high-dimensional vectors. These vectors capture semantic meaning, which allows AI models to understand relationships between different pieces of text. For example, let's say that you have words king and queen in traditional one-hot encoding, so a basic way of representing words as vectors. These words would be represented as completely different and unrelated entities. But with embeddings, king and queen might be represented as vectors that are very close to each other in the vector space because they share similar meanings, both being royalty. On the other hand, a word like apple would be far away from both king and queen, since it has a completely different meaning. But how do these embeddings work? To understand how they work, let's dive into an example directly related to our cooking books case study. Imagine that you have a recipe for apple pie. Each word and phrase of that recipe, like flour, sugar, apple slices, bake at 350 degrees Fahrenheit, can be represented by an embedding. These embeddings are vectors, which might be hundreds of dimensions long, that capture not just the meaning of the individual words, but also their context within the recipe. So at which point are they referenced? For example, the phrase apple slices in the context of an apple pie will generate an embedding that is closely associated with the other terms like sugar and cinnamon. This is because these ingredients often appear together in apple pie recipes, creating a context where their embeddings are related. However, if you have a different recipe, say, for example, pumpkin pie, the phrase pumpkin puree would generate an embedding that is close to cinnamon and nutmeg, but not apple slices. Now, let's see how this plays out in practice. Say that you have two recipes, one for apple pie and the other one for, pumpkin pie. Both recipes share common ingredients, flour, sugar, butter, but they also have unique ingredients like, apples for the first and pumpkin puree for the second. When these recipes are converted into embeddings, the shared ingredients will create vectors that are somewhat similar, but the unique ingredients will differentiate them. Now, let's go and take a step further here and look at it step by step. We first have the text preparation. So you take the raw text data, let's say the ingredient list, the cooking instructions for each recipe. you'll tokenize this text, breaking it down into smaller chunks like words or sentences. Then embedding, you'll take a pre-trained model. So let's say OpenAI embedding. So the ones that we'll use, there's the large, small, there's the ADA, and we convert each tokenized piece of text into a vector. For instance, the phrase 1 cup of sugar might be transformed into a 768-dimensional vector. This is massive. You cannot even, imagine this, where each number represents some aspect of the phrase's meaning. Then, once all of your text has been converted into vectors, we can map out into a high-dimensional space. So recipes with a high similar content will have vectors that are close together in this space. For example, chocolate cake and vanilla cake will likely end up being next to each other, while beef stew might be, completely different part of the space. Then we'd have using embeddings for retrieval. So let's say that a user queries your system with gluten-free cake recipes. The query itself is transformed into an embedding. The system then searches the vector space for recipes that are close to this query embedding. If you have correctly tagged certain cakes as gluten-free during the pre-processing step, those recipes will be prioritized into the results, while others will be ranked lower or even excluded. If we look into practical applications to make even this more concrete, so one real example is recommendation systems. So imagine that you're running a recipe website. When a user likes a particular recipe, your system can recommend other recipes that have similar embeddings. So if someone loves chocolate chip cookies, the system might suggest double chocolate brownies or peanut butter cookies because their embeddings are close in the vector space. We have as well semantic search. So embeddings allow for more intelligent search functionality. So instead of just searching for exact keyword matches, your system can understand the intent behind the query. For instance, a search for quick dinner ideas could return recipes labeled 20-minute meals or easy weeknight dinners, even if the exact phrase wasn't used. And then the most important thing is contextual understanding. So let's say your system needs to differentiate between Apple as the fruit and Apple as the tech company. Embeddings allow the model to pick up on these nuances based on the surrounding text. So Apple Pie and Apple iPhone would end up in very different embeddings, even though they share the same word. And to conclude, embeddings are powerful, and hopefully you now should have a solid understanding of what they are and how they work. And in the context of our cooking books case study, embeddings allow us to build a system that doesn't just retrieve information, but understands and processes it in a way that's meaningful. This is it, and I'll see you in the next video. Welcome back. In this video, we're going to do embeddings, but before we get to it, I realized that I forgot something. I do want to store or to save our filtered recipes so that we don't, need to go through it all over again, call the API and so on. And so define the output file path. So output file would be, filtered info JSON. One thing here, so enter the prompt, y store files as JSON. Sometimes I ask here because sometimes I don't know everything about something specific, and specifically here to JSON. It's not really a data type that I'm accustomed to, but what it says here, so storing data as JSON is useful. So structured data impose a clear structure on the extracted recipe information. It's human readable, apparently, and interoperability, so widely supported standard format, compatibility with RAG. So we would use here this format. So output file would then write the filtered list to a JSON file. Here we go. So with open, and yeah, let me take the shortcut. So output file, we use W for write as JSON file. And so JSON dot dump filtered recipes JSON file. And then I have here indent equals to 4 or to 2. What is this indent? So in Python, whenever you are indenting something, you can have 2. This is Google Colab. 2 is the standard, or 4. 4 is the most common in most of the other softwares. But Google Colab accepts 2. So we can have 4. So this is something that is going to work everywhere. And that is it. So let me do Control Enter. And we should have this recipe info. Recipe should be here. Recipe info dot JSON. And kind of works like a dictionary. Over here we have the indentation, as you can see. And this is very easily accessible. Now, the main topic, embeddings. This is going to be very easy. First things first, let me import libraries. And which one? One that we use all the time. So import numpy as np, shift enter. I'm going to load. Technically, we don't need to load, but I'm going to load the filtered recipes. And with open, and then we have our recipe info, .json, and then R for read as JSON file, filtered recipes equals JSON.load JSON file. Here we go. And here we go. Spelling mistake. Recipe info. Now we have it. We're going to generate embeddings for each recipe. Here we go. So recipe texts equals recipe info for recipe in filtered recipes. If we have a look here at, let's go to page 23, which is the one that we have been using the most. Have in mind that this is per page, not per recipe. So we need to have this in mind. Another way that we could try to improve this, and I'm going to write it down, is that we could have stored, instead of per page, per recipe. We could have organized this differently. So let me add here as an option. Another option would be to organize per recipe, but it should be done in the pre-processing. So like in the system prompt, you'd say, okay, organize per recipe. And therefore we would then, add recipes, which would pose quite a bit of other, challenges for us. For instance, what happens if a recipe is in between pages? There's really a lot that we can play around. So we have the recipe text. If we have a look at our recipe text here, let me do Control Enter. We have, all of it here, and it's quite a bit of text. But here we go. So all of them are here. And then what we do is we go and we get this embedding response equals to, we use clients dot embeddings dot create. Here we go. Input equals to our recipe text. model. We're not going to use this one. I'm going to search, so embedding models OpenAI. We can have a look. And embeddings. And how to get embedding models. There's currently 3 models as I'm recording this: small, large, and ADA. I'm going to use the large. You have pages per dollar, so you can see, for instance, if you use the small, for $1 you could do 62.5k pages. It's massive. I would recall that we have 100 something pages, so not a lot. Going to use this one. Embeddings is an important part, so I really want us to do well here. So I'm going to use the large, even though it's slightly more expensive, but this performance is apparently much better, or slightly better. So this is our model that we're going to use. Oopsie. Okay. Apparently I did something wrong. I misclicked somewhere. Control C again, Control V. And let me do Shift Enter. This I move up so that there's this note here. Now here, I'm going to extract the embeddings. Let's have a look. So we have our embeddings response. Control Enter. Something is wrong. Let me try again. So, embedding response. This is how I called it in the end. Control Enter. And it's very big. It's very, very big. But there's something that I want to show you to you. So here we go. Quite a bit of embeddings. Total tokens. 33k, something like that. And okay, let me go above. And almost there. Here we go. So create embedding response. Therefore, if I go here and I do dot data, this is where I actually, I'm able to get just the embeddings. Let me try to show it to you again. And here we go. So embedding, and we still have this. Now I'm going to store this under embeddings. Embeddings equals, what I do is data dot embedding, because I need to get this, for data in embedding response dot data. Oopsie, not this. Dot data, and then if I have a look at our embeddings now, you can have a quick preview to what is happening. And quite a bit of them. But this is how we need to organize them in the end. So we have quite a few of them. We have this now list, and now this is organized in a way that needs to be almost. Last thing that I need to do in order for this to be complete, I'm going to convert the embeddings to a NumPy array. This is going to make it effective when it comes to feeding to our retrieval model. So embedding matrix equals our NumPy array embeddings. Can have a look at our embedding matrix. You can also see it was way faster now to actually get an output. So you could see the difference when it comes to this, speed efficiency or memory efficiency. And then we're going to verify the embedding matrix, so print with an F string, generated embeddings for, and yeah, so the length of filtered recipes. So print each embedding of size like this, but something is off like this. And let me do Control Enter. Okay. And what am I missing? Potentially, actually, so curly brackets should come here maybe? No. Here we go. And now parentheses here. So we have 116 recipes, each embedding of size 3072. You may have more recipes, you may have less pages. It really depends, and this is a flaw here, right? So I've done this where I had 118 recipes. Because there's some stuff, and like in the pages, it's very important that you understand your data and have like a general understanding of what you're doing. And so up until page 87, we have recipes. And here we have potato soup. And you can see here that we have our problem with recipes that come from the other page. I'm not going to tackle that. Not the current goal here. That's a different purpose. But for instance, we have here in the appendix some tips, right? So we still have some kind of like title here. So this could potentially be included. It really depends on our system prompt and as well on how our system prompt then actually retrieved the information. Try to set the temperature set to 0 so that we have very little creativity, but still there's always a possibility that we get different results each time that we run the process, and this is a flaw. Let me add, so each time we retrieve information, we may get different results. Now, I'm going to stop here. We're done with this video. Next one, we're going to focus on our retrieval system. I'll see you then. Welcome back. In this video, we're going to focus on our retrieval system. Let me add here, retrieval system. We start by installing FAISS CPU, and here we go. So this is the first step. Then I'm going to import FAISS, and then I'm going to initialize the FAISS index. So index equals to, use the FAISS dot, and then index flat L2, index with a capital I, index flat L2, and then embeddings matrix shape 1. What is this exactly? So print the embeddings matrix shape. Here you go. So print. Here we go. So embedding shape matrix, embedding matrix shape. That is the right way. So we have 116 recipes, 3072 embeddings, and this is taking an odd amount of seconds to run, but this is our shape. And when we include one here, I guess, actually I'm not sure, but it should be connected to the number of embeddings. No, well, that's stupid. So it should be connected to the number of, like, to the length of the embedding itself. Yeah, exactly. So 116, and then the shapes should be 3072. And then what we do here is that we take the index and we do .add, and then embedding matrix, shift enter, and it should be matrix and not metrics. Here we go. Okay, so this is done. And here we go. We can also save the index. So save the index here. So FAISS dot write index. We include the index, and then, you know, filtered recipe index dot index. So it's always a good option when it comes to like dealing with page stuff, like save. And now we also save the metadata. Why is this relevant? It's relevant when it comes to having a look at our retrieval system. Is it working? And then we try to see whether the query gets the right embeddings, but how do we do this, right? So we can have a look at the data that led to the embeddings, and then we can have a look at the actual outcome, see, you know, if it's a good match. And then we can also add this to the RAG, right? So at the very end, we have the query, we have what was generated, because that's the output, but we can have this in-between step where we look at the metadata and see if from the metadata to the generation, if this is something that's, you know, reasonable. So save the metadata. So metadata, and here we go. Okay, equals to, and then we're going to save the recipe info, and here we go to the recipe and we get the recipe info. Here we go, comma, we get the image path so that we understand where is it coming from, and this comes from the recipe image path. Here we go, and then for recipe in, and this will be the, what was the name of it? Filtered recipes. Exactly. Here you go. You can have a quick preview at our metadata and see how it works. Metadata. Here we go. So this is going to be very, very useful to access. Okay, I went where I did not want, but this is a very nice way to organize and to store, and then in the end to retrieve. So we have the metadata, and then what we should definitely do as well is, you know, save this. So with open recipe, okay, recipe meta data dot JSON. Yeah, let me take here as JSON file, JSON dump metadata JSON file indent equals to 4, and here we go. We do shift enter, and we should see this recipe. Oops, should be in the previous folder. Let me see. So recipe metadata, and this would actually be very similar or almost the same as our filtered recipe. Okay, not this. We stored something in JSON before, if I recall correctly. Okay, here you go. Define the output file. This should be slightly different. So let's have a look here now. And we are going, or better yet, not in this video. I think we have been here for a while. In the next one, we are going to define a function to query the embeddings, but only in the next video. This is it. I'll see you then. Welcome back. In this video, we're going to query, but now based on embeddings. So define query embeddings. We're going to give it the query, the index. Metadata is optional, but highly recommended. Why optional? I mean, it's metadata. We don't need it, but it's good to have it, especially if we're doing debugging, as we should, because we're starting out. We start, so we're going to give you the steps, generate the embeddings for the query. We're then going to search the FAISS index. We are going to store the indices and distances. We are going to print everything. So indices, distances, metadata. And the aim here is debugging. Let's make sure that we see what our system is doing. And then we're going to return the results. And let's kick it off. Generate the embeddings. We start with query embedding. So equals to. This is actually exactly it. So clients embeddings create, input equals here the query, we get the data, we get the embedding. So very similar when we did here the embeddings, but now pretty much streamlined. Create, input, query, model. This one, we get the date and we get just the embedding. So this is step one. And this is an extra step, so we need to rework this as a NumPy array. So query vector equals to NumPy array. We include here the query embedding. And actually, now that I think of it, before I build a function, let me do this step by step here for you. And let me set, so query equals how to make bread. We have the query embedding. Let's print the query embedding. Here we go. So this is step one. Print with an F string. The query embedding is curly brackets, query embedding, and then /n. But this should be inside of the quotes, /n. And NumPy array, query embedding. Let's do Control Enter. And here you go. So we have the query embedding. And then we do this NumPy array. And if we have, so print a string, query vector is query vector. Let me give it /n. See that it is slightly different. Where did we have here our matrix? Here we go. Slightly different. And here it's recommended that you do dot reshape 1 minus 1, Control Enter. And this reshapes it in a way that's similar to what we had. Then we search the FAISS index, distances, so distances, and then indices, we use the index to search. Let's take this, so query vector, and in here let's do, instead of top k or just top k, let's do this minimum of the, what did I call it, the minimum of k, or the length of the metadata. And what is this? This is a debugging, right? So imagine that we look for the top 5, but we just have 4 of metadata, or we look for the top 50, but we have 40 in the metadata. It would throw an error. Therefore, let's set here as a minimum. So k equals to 5, Control Enter. How to make bread? Then we have the distances, we have the indices, and these would be the main ones that we would get. And then we would then print the, or I actually just want to print the metadata now. Print the metadata content. Here we go. Let me add here, so print fstring, the metadata content is, here we go. And then here, what I would do, it would be for I dist in, I'm going to zip the indices and the distances. Here you go. So if 0 less than I and less than the length of the metadata, print distances and then print the metadata. Control Enter. We have here a tiny error that we need to work on. So the truth value of an array with more than one element is ambiguous. So we need to focus on that. So metadata I, and here, let me just get the recipe info. Here we go. And here we go. Let me do Control Enter now. Still getting an error. I actually wonder what is happening. So if 0, so for I dist in zip indices and distances. So I go through it, and then until basically I get to the metadata, I'm going to print the distance and the metadata. This is a spelling mistake. So let's see. Still is not working. Let me explain here the error, because I'm at a loss what could be wrong. I actually really wonder if sometimes you spot my errors immediately, or you're like me and like you also cannot see. And okay. All right. Okay. I went a bit off topic. Here we go. I should have done something else here. Let me actually do it. And So I have the distances and the indexes, and I skipped this step. I should store the indices and distances. So stored indices equals to, I go to my indices, 0 to list, and here you go. So let's see how this works. And then here it should be stored indices, and here you go. Because you have here the distances, it's a list inside a list. Same thing for the indices. And stored distances. So Control Enter. And here we go. We have everything. Let's have a look. So we start here by printing the query embedding and the query vector. And then we come here, we have the query embedding and the query vector. And then what we go is that we go and we take this and we come here to the FAISS. And then we get the distances and the index. Then we get here a list inside the list and the same. And then what we do is that, okay, this is not going to work. So let me just have one list. And this is where the store indices and the store distances come from. And then what we do is that, okay, let's take each of them and let's get the metadata. So for the first one, distance is 1.13, and here's the structured information. And then here we have the breadth. So we have everything related to that metadata. And towards the very end, we need to return the results. So results equals, and we have our metadata, and this will do for I. So this will be a loop. We have here our recipe info, and then specifically the dist for I, dist in zip, and here it should be stored indices, and okay, stored indices, stored distances. Here you go. Let me triple check. Here you go. And then here, so if 0 less than or equal to I less than the length of the metadata. Potentially, it could be optimal to have done this here above, but for some reason, I split it. Potentially because in one, we're focusing on printing, the other one, we're focusing on storing. And let me get here the results. It's invalid syntax. And why is it a invalid metadata? For I dist, okay, I'm missing here parenthesis. For I dist, and this is one parenthesis too many here at the end. Control Enter. Here you go. And then what we have at the end is that we have stored the metadata, and we have stored as well the distances. Now, let me bring this up. So we have this, and now let me get all of this, and I'm going to put it here. So Control V, and let me replace what needs to be replaced, and let me reorganize this part. This is a debugging. Let's not print the metadata. And I guess we don't need this because we have the stored stuff, or better yet, let me put it here as a comment, and query here. I'm going to have it here to test the function. I don't need. So then I grab everything, give it a tap, come here, return results, shift enter, going here to test the retrieval system, and then results, query embeddings, query index metadata, and then I would print with an F string the results are, and then results. Control enter, and here we have it, right? So we have here the information, they have the embeddings, and this is what it comes from, right? So we get the stuff from the metadata at the very end. And this is how it is supposed to be. Now, what we need to do is that we need to take this metadata and all of this information and bring it to our generative AI model. But that's in the next video. I'll see you then. Welcome back. This is going to be a very light-hearted video. We want to have something that combines the results. If we have a look here at our results, so length of results, we have 5 different results. And what we need to do is that we need to merge everything to feed to our GPT. Here we go. So we go and do it, define, and then combined retrieve content, and we get here our results, and we have combined content. And what we do is that we are going to join this, and we are going to do result 0 for result in results. Let's have a look. Let's have a look at our results so that we have a clear view at what we're doing. If you look here, this is what we're doing. So then 1, and then 2, and all of them are different for all of them. And so we go and we do, so this is 0, but what it does is that it goes through, the 5 of them. So for all of them, so join this for result in results, but this is not joined. So how do I do it? We have this string, and what we do, or what we can do, is that we add here an, oopsie, also not this, here we go, n. So we join, but we add 2 lines in between. And here we go. And then what we do is that we then apply our function here. So we would have combined content equals to combined retrieved content results. Let's do Control Enter. And here we have it. So this is our output. And this is absolutely it. Let me just triple check. Yeah, this is exactly what I wanted to show you. So next time we go with our generative system. And that will be it. Till next video, have fun. Welcome back. In this video, we're going to focus on the generative system. This is a 3-part process. The first one, probably the most important, is to define the system prompt. And so this is the first one. Second is to define function to retrieve from the API. And step number 3 get the results, the easiest one for us. And let's come here to the function. So define generate response. And here we include our query, our combined content, and our system prompt. And then we can kick it off. Response equals, let me get here the shortcut, model equals model, messages, role, system, content, system prompt, role, user, content, and this should be something more towards, just a query even. The query. And here we go. Let me close here curly brackets. And then, role, assistant, content, combined content, temperature is 0. And then we return choices, message, and the content. Let's do Shift Enter. And our query is the query here. This is the one that we're going to use. Then we have the combined content. This we defined in the last video. And the system prompt we have defined too, but this is a different one. So we are going to define our system prompt 3 equals 2. And then here we start by defining, right? So first thing, let's give it a persona. So you are a highly experienced and expert chef, specialized in providing cooking advice. First one, your main task. So let's give it a task. Your main task is to provide information precise and accurate on the combined content. And we can continue. So one thing that we may add, so you answer directly to the query using only information from the provided content. To reinforce, we can as well, let's give it a try, why not? Or better yet, not specifically here, but you could add from the combined content. So for instance, you put here an F, right? So here, combined content. Let's actually give it a try. I don't have it on my system prompt that I specified initially, but let's give it a try. If you don't know the answer, just say that you don't know. And yeah, your goal is to help the user and answer the query. And then here, query. Let's give it a try. System prompt 3. And let's get the results. And yeah, let's take this. It's always good to have everything in one. And then, get GPT response. And here we have it. Now that, I included this. This was not part of my initial plan. So what I'll do is that first I'll fix the error, but then we're going to try a bunch of stuff. str object has no attribute choices. Why is that? So get GPT response, because we have done this before. Question is, what is wrong? And we have done so much that, so get GPT response. So response equals to this, get GPT response. Something looks weird. So response choices message. Okay. Let me get here our response. The error was in the GPT response. So let's try again. Potentially there's something that is weird here. Let me actually triple check. So response choices message content. Model equals model. System content, system prompt 3. System prompt 3 is defined. Role user content query. Role assistant content combined content. Now it worked. Okay. And then get GPT response. Not this. In case that it throws an error. Okay, so something is odd here. So let me do Shift Enter. Here I want to display the outcome, but I need to evaluate here our response to see, what is up. And here we go. So to make bread. You know what I think it is? So where did we have? So I think it was here that we built the function. So when we did it, so response, and then we would have GPT response, which we would then include here. So I just need to have this response. Yeah, we transform it there. Okay. So what I need to do, so let me do Shift Enter here. And here we go. Get GPT response. And why this is an error and I'm not, seeing it, it's because like this part about having a function for the display markdown, this was something that I was like, yeah, let me do this, in between while I was recording. I thought it was much better idea. But when you have much better ideas, you're also very much prone to throwing an error. And here we have like a bunch of different functions, right? So, or better yet, you have a bunch of different recipes that you can do. They're very well organized. So query how to make bread. You have like a lot of stuff like corn, bread, yes, corn milk, flour, corn bread, brown bread, graham bread, oatmeal bread, nut bread, Boston brown bread, bannocks. Do you know what are bannocks? No clue. So basically we have so many possibilities. So this is really a matter of giving it a try. And there's just so many possibilities. So for instance, another one, let me actually go here below. So for instance, you can be specific here, and because currently we're just getting everything from our metadata and getting the results. So get me one, or get me the most relevant, and then here you would include chocolate cake. The most relevant is like the worst query. Get me the best chocolate cake recipe. Let me do Control Enter. and below as well. This I don't need. I'm sorry, but I don't have a chocolate cake recipe available. This is interesting. And now let's triple check. Let's get here chocolate cake as a query. Control Enter. And query vector. Do we have chocolate sauce? Okay, this is, I have no clue what this is, but okay, let me do Control F here, Control A, Control F, chocolate. So chocolate, chocolate sauce, chocolate pudding, sauce for chocolate pudding, chocolate sauce, chocolate sauce, chocolate taffy, squares of chocolate. Very cool. So I like that. It answered exactly as it should. So very, very cool. And but now that I think of it, this was stupid. So get me the best chocolate cake recipe. I'm using the combined content of the bread. So, okay, negative points for me for not understanding this. I was treating this immediately like a RAG, but not. We're just focusing on the generation for that specific query. That will be in the next video, I promise. This is a mea culpa. The next video, we are going to focus on our RAG system. And that's, really why we're here. I'll see you then. Welcome back. In this video, we're now going to build our RAG system. So our RAG system. So define our RAG system. Like, what do we need to include? So if we come here to our retrieval, where is it? Here we go. So we need to include at least this, and come back down. So query index metadata k equals to 5. And then if we go to our generative system, we need the system prompt for sure. Query is there. Combined content, I will actually include it in the actual function, because if you think about it, before we have the combined content, we need to get the content, and therefore it's easier to combine it in the function itself. K equals to 5, and then system prompt. Here you go, close parenthesis, colon. Let me start here. So we start. There is the retrieval system. There's the content merge. And then there's the generation. Here we go. So let's go with the retrieval system. So results, query, embeddings. Okay, this will actually go here to the content merge. So generation, combined content. So we have the query embeddings, query index, metadata, and then we have metadata, and we have the K. And then we have the content merge, combined content, combine retrieved content results. And then we have the generation. So response equals to this, and then we return the response. Let me add, so build the function for RAG. And here we go. Here, yeah, so all of this is working. For some reason, there's an error there. Okay, non-default argument okay. So when it comes to arguments, you should always include what is mandatory at the start and what is optional at the end. Shift enter. Here we go. Let's test this. So test the RAG system, query 1, how to make the best chocolate cake. And then we would have our RAG system. And actually, so answer equals to this. RAG system, we would have our query 1, index, our metadata, our system prompt 3, and okay, printing a lot of stuff. I'm not sure I 100% want all of this, but this is a possibility. Let me get here, get GPT response answer. Okay, no positional arguments, but 1 was given. Okay, let me, or better yet, so the simplest one is that I just change this to response. And then here we go. Then the answer goes, sorry, don't have a specific recipe for chocolate cake. You can also see here the distances, but it's very cool, right? Even though it may seem that we don't have a lot of, or the distances that are tiny, and we can try it with some other query that will work. The LLM is still able to say, hey, this is not answering your query. Therefore, test with a different query. So query 2 here would be something like, I want something vegan. Let's see how this works. Query 2, get GPT response. We have the stored distances, vegan banana bread, very good. And this is actually what I wanted to point out, right? So the distances here are from 1.19 to 1.3, but, and here they're far larger, so 1.4 at least, but because we do have a lot of stuff with chocolate, but not necessarily chocolate cake, our LLM is basically saying, hey, we don't have it, but we do have the vegan banana bread. So I think this is very cool, and I'm very happy that this worked. It was the whole goal all along. And just to wrap it up, just so that you see what we have achieved, right? So we went from one book to images, embeddings, retrieval system, the generative system, and then finally the RAG system. And it was such a lengthy job that we did, but we managed and we're here. And this is where we reach a level that we are good. And now from here on out, we go to the next level. So we go from being proficient in RAG to go to a expert level RAG, or at least to start in that track. I'll see you in the next video. Alrighty, so I'm going to show you something here, and I'm going to record this knowing that this will be removed. And like the bottom line is that it's not super important for application because this, what is going to be removed, uses the 3.5. But this part here has a very cool feature that I'm very sorry that is going to be missed, which is the probabilities. And this is the easiest way that I have found to show you probabilities and tokens and how they are connected. And specifically for this video, I want to play around with the top P, which is a parameter that I've shared that it's whatever, but it serves a purpose. So let me show it to you and let's see how this works. We're going to use our dices here. Your task is to roll the dice. Let's try it. Submit. Okay, it's not a good output. Let me see. Maximum length. Okay, let's, change this to whatever. 100 tokens. Let me try again. Submit. Okay, not what I want. So let me start with a different input. Roll the dice and tell me the outcome. Let's try like this. Okay. And tell me the outcome. Let's try it differently. Okay, I rolled a 5. Let's play around with this. We see here that we have as a probability, that's 4 has 41% probability and 5 has 26. Now let's play around with this. Take note of the 44%. I'm going to get here our top P to 40. And I rolled a 4. Okay, let's have a look at it. 44%. Let's try again. And I rolled a 4. You see here, our probability is 44%. And I set the top P to the top 40%. This means that I cannot, or the LLM will not consider anything but the 4. The 4 will always be the next outcome. And this is how you can influence an LLM. Now, this is crazy specific, but this is the purpose of the top P. You must really make sure that you want, that, right? So it's very specific. Now let's change here to top P, 51. And here we start having the 4 and the 5. And it can even happen that we actually get a 5. That, just I would really hope. And we get a 5. Yay. So, but if we decrease again, and then we go and I roll the 4. Here we go. And let me just do it, 10 times so that you see that out of all these possibilities, it's always a 4. Here we go. That's the purpose. So for showcasing this, very cool. For the rest, it's whatever. Did I do 10 already? Okay, I think you get the purpose. And okay, I'm going to keep this, I think I love this example. I'm going to keep this even after March 15, 2025, which is actually right around the corner. But the thing is that unless I find another playground to show you these probabilities, this is going to be, if you know of any like this, you can see the probabilities and it's crazy easy and intuitive. Let me know. I'll be very keen on making sure that you can use this. But for now, I'm going to leave it as is. I'll see you in the next video. Get ready for Multimodal RAG. In this section, you're not just learning concepts, you're gaining skills to build systems that can process and understand diverse types of data, like, text, audio, images. So imagine a world where AI can seamlessly combine these modalities to generate coherent and context-aware content. That's really like the power of Multimodal RAG. And by the end of this section, you'll have hands-on experience in creating it. Now, I want to tell you, I think this section is fantastic. We're diving into one of the most cutting-edge areas of AI, the ability to integrate various types of data, like text, images, etc. And this enables us to create rich, informative, and relevant outputs. Think of it, right? How often do we as humans rely on multiple senses to make decisions or understand the world around us, right? So we hear, we speak, we gesticulate, we smell, there's so many senses. And Multimodal RAG brings this human-like capability to machines and allows them to perform more sophisticated tasks. So we are pushing our boundaries. Let me cover our learning objectives and outcomes for this action. So, of course, the most important is multimodal integration, how to combine various types of data. And it's not, processing them. I mean, it is, but it's about creating a system where each enhances the other. So images enhance text. Audio, leads to text, or audio with images. This one is still not so well developed. So we need to go from audio to text and then talk to images. As well, we're going to build real-world applications. So we're going to extract frames from a video, transcribing audio with a whisper model, and then merge them together. We're going to leverage AI models. So I've talked about the whisper model. We're also going to use the clip model for understanding and aligning images and text. You learn how to use these models to create embeddings and performed data comparisons. As well, contrastive learning. So what is this? This is when we try to see what kind of text is similar to what kind of images. And this allows us to fine-tune our RAG models. And lastly, we're going to create interactive AI systems. So based on what we have, so let's say we take a video, we're able to create a RAG system out of it. This is also something that's highly in development. So multimodal RAG, I think, maybe this is something that may get outdated. If it is, let me know. If there's something new, let me know, because this is a very cool thing. And the future of AI is multimodal. And therefore, we need to build these AI systems that also leverage multimodal data. That's it. Let's get ready. I'll see you in the next video. Let's explore a bit more multimodal, both RAG, but with a focus on GenAI. So imagine that you're part of a marketing team and a company launching a new product. You need to craft a campaign that uses information from multiple sources, so text documents with product specs, customer feedback videos, competitor images, audio clips from focus groups. Each piece of data holds valuable insights. You don't have the time to manually sift through all these formats, extract key points, create a compelling narrative. You need a tool that can pull insights from all of these formats quickly and cohesively. And this is where multimodal GenAI comes in. Let's have a look at this image. The goal is that you take several inputs and then it leads to outputs. And currently, so this part, so text, image, audio, and on both sides is very good. We're starting to have good developments in reading video as well. The production of video, this is something that will take a bit of time. It's far more complex. We'll see good stuff for short clips for a while, but until we can have a proper amount of video, that will take a while. Also, in my perspective, some images are good, but usually it's a very frustrating thing to try to get images. But the understanding, so the input part, this is very good. When it comes to the video, which will be the focus for us, one very good workaround is the one that we'll use, which is to have images, so frames and text. So what we need to understand when it comes to multimodal AI is that this is like multitasking. And this is very similar to how we might read a document, analyze a chart, listen to a speech, watch a video, all while making sense of how these different pieces of information fit together. Here's how it works. So you provide AI with a text, with document features, or with product features, a series of competitor images showcasing their latest designs, customer feedback videos, audio recordings. And then the model processes each type of data through specialized neural networks. So text is handled by natural language processing techniques, images go through convolutional neural networks, audio is analyzed using spectrograms, and video is, frame by frame in order to understand the visual context. And then after processing each modality, the AI synthesizes the information to create a cohesive marketing strategy. So it identifies key selling points from the text, spots design trends from competitor images, captures emotional tones from audio clips, and summarizes customer sentiments from videos. Then the challenge is, how do we integrate all of this? So we now explore how to work this multimodal within our RAG systems. In a multimodal RAG, this means it can retrieve and generate content across various data types, significantly enhancing its ability to understand. For us, we're going to focus on retrieving images and audio and generating text. So if we consider our marketing example again, instead of providing isolated pieces of information, multimodal RAG retrieves the most relevant insights from customer feedback videos, couples them with key design elements from competitor photos, and generates a comprehensive report that offers a complete understanding of the market. But of course, at the same time, there's also challenges here. It's really not that easy to do because all data types have their own challenges. So for instance, text needs to be tokenized and embedded. Images require feature extraction through techniques like convolution. Audio must be transformed to a format that the AI can understand. And video involves processing both visual and audio components. And then synchronizing all of these processes is also a challenge. So the AI must accurately interpret and integrate all this information in real time. Moreover, the ability and relevance of different data types can vary. So video feedback might offer more nuanced insights than text reviews, but it's also harder to analyze due to factors like background noise or poor lighting. And then the RAG system does need to weigh all of these factors, deciding which ones are relevant, and then blend everything at the end. To conclude, while multimodal AI and RAG systems bring remarkable capabilities, they also require advanced techniques to manage the complexities. For a marketing team, this means moving toward the future where you can instantly synthesize vast amounts of data to craft strategies, to go to market with products, or to analyze customers. But this is an exciting time, and as technologies are advancing, like, the potential just gets bigger and bigger. That's at least my perspective. Super excited to share this with you. I'll see you in the next video. Welcome to this first practice video on multimodal RAG. Please come to the RAG folder and then multimodal RAG. It's going to be a fun one. I have here one of my crash courses that I have live on YouTube, and you can see by my face here, one of my first videos that I recorded here in this tiny corner. It is 1 hour-ish, and I specifically chose a video that was 1 hour-ish because there are some challenges that a 1 hour video has that a 3-minute video do not. So this is what we need to pick. And why is this multimodal? So video, of course, but at least, currently the AIs cannot really read video, and definitely not video that is 1 hour long. And I think it will be that for, well, a bit of time, because it's quite, there's a lot of information in a video. And what we are going to do is that we're going to split the video into audio and to frames or images. And this audio/frame is the multimodal, because we're going to feed both into our model. And even if you think from a perspective of a video, it's also multimodal. So you'd have the video part, which is, the several frames per second, and then you also have the audio. So this is where we really take a lot of what we have learned and try to make something out of it. Now, this multimodal is still very much in development. The technologies are there, but in a way that it takes to process everything from a computational perspective, it's tough. So there's quite a few challenges that are there, and this is why the libraries, they're not so ready for multimodal stuff. Therefore, a lot of the things we need to build on our own, and that's okay. So because we need to build them ourselves, also get to learn step by step how they work. So I've opened here a new Google Colab file. I'm going to call it Multimodal RAG, and this video is going to be dedicated for the setup. So let me first mount the drive, and let me add here, let me call it, step 1. There are 10 steps. Step 1 and step 2 we do in this video. All the others will take a bit more time. And so let me get here. So let me activate the GenAI course key. Let me copy this code. So this one is called GenAI course. And let me call it API key equals to this. And so this I can close. This I can do Shift Enter. Can now increase our visibility and mount the Google Drive. And it will be %cd something. Still waiting, but yeah, popped drive and then my drive. And then the GenAI course RAG and then multimodal RAG. Copy the path, Control V, and then Shift Enter. So this is step 1. Step 2. Oops, I actually wanted this. I initially intended to show you how to download a YouTube video using Python, but I actually had quite a bit of issues in the end. So I opted to just give it to you. You can always download it from YouTube if you have especially YouTube Premium. But in the end, it's always easier if you have the stuff in your own directory. We are going to define here the video path. So video path here, this is equal to, and decision making course.mp4. Step 2 is to get the data. And that is it. So step 1, step 2, very easy. Step 3, will not be as easy, but I'll see you then. Welcome back. In this video, we're going to do part 1 of the audio extraction. And next video is compressing, but on that later. First, we need to install libraries. So first and foremost, pip install. And the one that we need to install first would be the PyDub. Let's add here the Q for quiet. And then apt get, and then install the FFM pack. And this is what is going to allow to extract the audio. We're going to build a command with that specific library. We then need to import the libraries here. And we import OS. We import the subprocess, and then from PyDub import audio segment, and that is it. Then we need to define the audio path. So audio output path equals to, and then we have this audios, and then output dot mp3. Shift enter. We then ensure that the output directory exists. So in this case, we already have it here, and I'm going to leave it. But in the case that it didn't, you need to create it. And the way that we do it is that we set this, so OS path dir name, audio output path, and not this. And then what we do is if not, and then OS path exists, and then we include our output directory, we would make the directory. So this is step 2. Then we need to ensure the output file has the correct extension, and this is simply, so if not audio output path ends with mp3, audio output path plus equal the mp3. And let me do shift enter. We have here our audios, and then eventually we'll have here our output. Then we construct the ffmpeg command to extract the audio. Here we go, command equals to square brackets, and we kick it off. Start with ffmpeg. So this command will be fed into this subprocess library, and this is what we installed, the possibility to build this command, and this is part that allows this audio extraction. We include this y. This is important. This basically does so overrides if the audio exists. Then we have this I, and this relates to the video path. Note that the video path comes from here. We have the video path, comma. This refers to the input file. Then we would have vn. This is including that we don't want video, so no video. Then we need the audio settings / codec. So a codec, comma, and then lib mp3 so MP3 lame, and these refer to the audio codecs, and then we would then include the audio output path, and this is the actual output file. Shift enter. Here we go. We would then execute the command to extract the audio. This is going to take around 1.5 minutes. So sub process command check equals to true, and we can do control enter. Tiny error. So command so this as a non-zero exit status. So IVN a codec lib mp3 lame audio output file, and okay, let me run this out video path again just in case, and the command, and see if it works. Otherwise, yeah, we definitely need to ask for help. Let's explain here the error. So there might be a type FFmpeg. Video path does exist. Audios output MP3. This is what we want to build. And here we go. FFmpeg. Did I import all the libraries? I did. Okay. Import subprocess from PyDub import audio segment. Okay, I'm a bit at a loss. We have the video path, which is here. So let me import everything again, see if it works. Okay, still does not work. Okay, let's ask ChatGPT, since the good people at Gemini are useless as usual. And here we go. Yeah, from here to here, Control C, Control V. And we can have a quick preview. There's few minor errors, okay. There's a typo, here we go. Should be a codec. So this was one. Code cleanup. Meh. So let's try again. Control enter. So yeah. Okay, negative points for Gemini for not being able to discover this. So it is running, so I'm going to stop this video here and I'll return the next one. We're going to talk about compressing audios, which is an important element in this data processing, especially for very, very long audios. I'll see you in the next video. Welcome back. So we have now completed this, 1 minute, 20 seconds, so not too long. And then if we have a look at our audios, then we'll see here. So output MP3. And if you play it.
Are you looking to improve the way that you make decisions? Do you sometimes worry
hopefully
that
can
you
hear
don't
this?
have all the tools to make?
There's like one thing that you need to have in mind, right? Which is the quality. And if all goes well when it comes to my audios, they should be high quality, point one. But the most important thing is how I store them. And I store them always in a very high bit rate. So actually, I don't even know what bitrate is, but it has to do with the quality in sound. What is bit rate in sound quality? And I can't answer this. Okay, this is a very good RAG. Okay, bit rate. Bit rate refers to the depth of information, whether in video or audio. So also in video, important to know. Measured as the amount of information per second. And I think my bit rate, so set the bit rate, and so set the bit rate. So my bit rate, this is around, I think 192, if I'm not mistaken. And what happens is that if we have more information, then we also will have more tokens. Remember that what we're doing is that we're taking this spectrogram, this audio, and this is the input for the Whisper model. And the more the information, then the more tokens. Therefore, with a 1 hour audio, this won't work. And I'm going to set it to 32. I think this will work. And as we'll see, so it either works or it doesn't work. And then if it doesn't work, we decrease to 16K or so. But have in mind that the current is 192. So we are already decreasing significantly our bit rate. And what I want to show you is, okay, this is our initial audio. This is our compressed audio. So set path for compressed audio. And then compress audio path, audios, and then compressed.mp3. So very good. Then we would construct again the ffm peg command to compress the audio. Compress the audio. Here we go. So command, let me take this. And so what I have is minus AB. I have Y for audio output path, compressed audio path, and let me add this Y for overwrite if needed. And this is it. Then we would execute, so sub process dot run command. So command and then check equals to true. Here we go. Let me do shift enter, and it's going to take a few seconds, but I'm going to stop this video here. Come back in the next one. I think now we need to go to the next step, which has to do with the Whisper model. So this is also exciting for us to learn. I'll see you then. In this video, we're going to dissect the Whisper model, which is a model specialized in speech recognition. It's designed to handle diverse accents, languages, and even background noise. If you've ever wondered how AI can transcribe conversations accurately in noisy environments or differentiate between multiple speakers, this is your answer, the Whisper model. First, let's have a look at the architecture here behind the model. We're going to break it down bit by bit from start to finish. Might seem confusing at first, but I'll try to make it as intuitive as possible. The journey starts here with the audio input, specifically the spectrogram. Think of this spectrogram as a visual representation of sound. Instead of just listening to the audio, Whisper transforms the sound into an image that captures different frequencies over time. It's like converting spoken words into a visual map that the AI can analyze, giving the model a structured way to interpret the speech. Next, it applies a convolutional neural network layer here. So it uses two one-dimensional layers, followed by this GLU or GLU, that stands for Gaussian Error Linear Unit. And this is to detect local patterns in the spectrogram, much like how convolutional layers in image recognition detect edges or textures. In the context of Whisper, these layers help identify critical features in the audio, such as accents. And then after the layers comes this sinusoidal positional encoding. Just as we learned with the transformers, positional encoding provides context about the position of each feature in the sequence. For Whisper, this encoding helps the model understand the temporal order of the audio signals, ensuring that the sequence of sounds, like words in a sentence, is accurately represented. Then we have encoder blocks. These are similar to those used in transformers, but adapted for audio. Each encoder processes the features further, applying multiple layers of attention and normalization to understand better the audio structure and content. And these blocks work together to build a good representation of the entire audio input. Then we have the cross-attention mechanism. This is actually where the magic is. So it allows the model to link the audio representations built by the encoder blocks with the tokens being generated by the decoder. Imagine it as a bridge that connects the understanding of the audio with the processes of generating text. Then let's have a quick summary here. So the Whisper model starts by transforming audio input into a visual representation called a log-mel spectrogram. This step allows the model to convert sound waves into an image format, capturing the different frequencies over time. Using one-dimensional convolutional neural networks, Whisper detects local patterns. This is crucial for distinguishing various voices and pronunciations. The model then applies sinusoidal positional encoding to maintain the order of sounds. After initial processing, Whisper uses encoder blocks to further refine the audio data. These blocks apply layers of attention and normalization to build a detailed understanding of the audio's structure. The key innovation in Whisper is its cross-attention mechanism, which acts as a bridge between the encoded audio data and the text generation process in the decoder. Next up, we have the decoder blocks. These are tasked with generating the transcription based off the encoded audio information. The decoder, much like in language models, predicts the next token in a sequence based on the previous tokens and the encoded audio data. It's a dynamic process where each block refines the output, moving from a rough transcription to a more polished and accurate version. At the bottom right of our diagram, you'll see how the output is prepared for the decoder using tokens in multitask training format. The Whisper model can handle various tasks from transcription to translation, and this flexibility is enabled by tokenization. Each token represents a chunk of speech data, like a word or a sound, and is embedded into a high-dimensional space that the model can work with. The learned positional encoding is then applied to these tokens to maintain the sequence. Learned positional encoding is then applied to these tokens to maintain the sequence information. Finally, the model moves to the next token prediction. This is where the Whisper outputs the final transcription, one token at a time, predicting the most likely next word based on all the processed data from previous steps. For example, if the audio says the quick brown fox, the model uses its understanding of the audio and language patterns to generate each word in sequence. And you can see here, right? So this is where we are currently. And then based on the learned patterns and also in the audio, then it tries to predict that the next one will be brown. Now let's sum it up. So Whisper's design makes it incredible versatile, handling everything from noisy environments to multiple languages and accents. Its strength lies in its ability to integrate multiple advanced components, from convolutional layers that interpret raw audio to cross-attention mechanisms that align audio understanding with text generation. This is an invaluable tool for real-world applications like automatic meeting transcription, multilingual support, and more. This is it. I'll see you in the next video. Until then, have fun. Welcome back. Before we start with the next step, which will be step 4, exactly, let me find here our compressed. If we have a quick view, I don't know if you recall how it sounded, but should be a div.
Are you looking to improve the way that you make decisions? Do you sometimes worry that you don't have all the tools?
I don't know if you can notice. It's still good, but it's grainier, you know. It's a bit more tough to hear. That's it. Let me continue. And let's go with step number 4. And our step number 4 is then to transcribe audio using OpenAI API. And we need to install, so pip install quietly the OpenAI. And okay, so this is done. Also, I didn't know you could have a space between the exclamation mark and the pip, but live and learn library. And then from OpenAI, import OpenAI. This we know already. We then connect the script to the API. This is done with our client. OpenAI API equals API key, or API key equals API key. And then what we do is that we open the compressed file in binary mode. So this shortens the amount of information. We use this with, and then this is exactly what we do, but let me kick it off. So we start with opening. We always need to open. This is sort of loading the audio into our script. Compressed. And then audio. Path. And then read binary. And then as file. Colon. And then we then use the whisper model to transcribe. And then we have this transcript. So transcript. This is very standard now, so client, but this complete is audio / transcriptions / dot create. And then we open, so model equals our whisper 1, and then file equals to file. This is how it works. This is roughly the same, and I'll show it to you later. But this process of with is that it's when you open and close a file at the same time. So we're now going to do the writing of the transcription, because now we currently have the transcription, and now we want to export the transcription. Let me do Shift Enter. It's now, it's basically transcribing now. And now I'm going to define the path where the transcription will be saved. So the transcription path, let's do transcriptions or transcripts and then slash transcript.txt. So transcript path, and this is still running, takes some time. It is a long audio. And now while this runs, we would then save the transcribed text to a file. And then we would go with open and then transcription path, transcript path. And it's actually like there's always like this, I don't know, I really want to press on tab because, you know, it feels like a shortcut. Same time, I worry sometimes a bit that you don't follow through with everything. So I try to write more. So what I do is that we open and then we're going to use this write because we want to put there different than this when we had read binary. It could also be just read, but for the sake of Whisper is read binary as file. And then here what we do is f or file dot write, and then we would write the transcript that we're getting from here, and then we use dot text. But I'm going to show it to you. This is, so the dot text is the attribute from transcription. Right, so this is how you get the text. Similar to when we have the OpenAI API and we have the content. Here we have the dot text. So it's done. And let me show it to you. So we would then inspect the transcript. And I don't even know why. I think this one, yeah, it was indented. So transcript, can kick it off. You can see that we have it here. We have the transcription, and then if we were to have dot text, then we would have just what was transcribed. We have this is done, and it's good to see that this is working. We then define the path, and then we save it. Or we don't save it. Transcript path, transcripts slash transcript dot txt. Why is this not working? Could be potentially that I need, here we go. I'm missing this part. I actually wonder why this is not included in my notes. So we have this output directory and transcript path. Here we go. And here we go. And then if not OS path exists, output directory, make output directory. Check here how this is going. And so this part is here. Very good. Let's try again. There you go. And let me, okay. This is still processing, I guess. This code is the same as this. So let me do save the transcribed text without using this, with. This will be the same as, having this file equals to open. Yeah. So transcript path, write, file, write. So this part is here, and then file close. Arguably, this one here is a far more elegant way of doing. this one, I would reckon that it's something that even if you're not so accustomed to Python, you look at it and you're like, well, it makes sense to me. You open, you write, you close. This one here, like the closing part is already there. This is, I think the width is a bit more of a when, at least in my perspective. So when this is open, we write, and then the ending or the closing is subintended. So let me add here as comment. So I'm not going to run this, but I am going to stop here in this area. Next one is step 5, which is to extract frames from the video. And this is it. So time to go to the next step. Until next video, have fun. Welcome back. Let's kick off this part where we extract the frames from the video. We need to install something, pip install, and it's this movie Pi, shift enter, and then load library, here we go, from movie pi.editor, I import the video file clip, define output folder, so output folder going to be frames, and then so if not os dot path exists, output folder os make directory with the output folder. Here we go. Let's do shift enter, and then we need to load the video. So this is something that is pre-prepared. So video file clip is the video path, and this video path was defined all the way in step 2. So here we go, shift enter, and now we extract the frames. And this is nothing. So we start with, frame path. So this is going to be an empty list. And then we have this interval, right? So why? Because we're not going to extract 1 frame per second. If you have in mind, I think my videos, most of them are 30 frames per second. Even like sometimes when I record this one, for instance, this is 60 frames per second. And therefore, this is quite a lot. And even 1 frame per second is massive, right? So I've been speaking for 10 seconds, the screen has not moved. So there's a lot of information that we don't need. Of course, we may lose some stuff, but that's part of it. This is why we also have the transcript. This transcript is supposed to be there to help. But I'm going to do, at each 10 seconds, I'm going to do 1 frame. So, second 1 frame, and then second 11, another frame. And therefore, this is what is more than enough. So for t in range, we go from 0 all the way to the video duration. So integer video dot duration, and we go at steps of interval, which is 10. Here we go. Sorry. So the interval, so video duration, parenthesis, interval, and then there's a parenthesis too much. We start by getting the frame path, and then os.path.join. We have the output folder, and then we have this f string where we're going to call it with a frame of t. So, second 10, so 10, 20, 30, and so on. T, but let's add it with 4 decimal case, so 0010, 0020, and so on. So 0 for D. And then .png, here we go. And then we save the frame at the specified time. And then it is video dot save frame. And what happens is that we, of course, have this save path at time t. And then we append everything. So frame paths dot append. This is more for the future, in case that we want to use them immediately. But basically, the saving is here, and then we also have it here in the frame paths. Let me do Shift Enter. And in general, it's very good that we save everything, because it's not that long. Sometimes it takes 1 minute, 2 minutes. I don't know how long this takes. Could take 5 minutes. But it's very important that we have a scalable product, and this is part of it. With this, we're absolutely done. Step 6 will be embedding audio. So this is the next one that we need to do, and I'll see you in the next video. Welcome back. In this video, we're going to cover contrastive learning and the role it plays in multimodal systems. In our context, contrastive learning helps align different types of data, such as audio and images, allowing the AI to understand and generate more contextually relevant content. Imagine that you're teaching an AI to process both what it sees and what it hears. This is where contrastive learning shines. Let's first cover the core concepts. So contrastive learning involves training a model to distinguish between similar and dissimilar data points across multiple modalities. Think of it as teaching an AI how to match the tone of a voice to a corresponding facial expression in a photo, or how to align a piece of spoken advice with the right visual context. By learning these associations, the model becomes better at integrating and generating responses that make sense across different types of inputs. Now let's zoom in to our case study, which is our crash course on decision making. We use contrastive learning to align audio descriptions of decision making with relevant images. And this allows the AI to understand the nuances between the several concepts that are covered. For instance, intuitive versus analytical, or system 1 and system 2, like covered in the crash course. And this is done by pairing audio with visual. Therefore, if we zoom in a bit more, so let's take a look here at this diagram. What we want to focus is we want to have positive pairs and we have negative pairs. And in this case, let's focus on our decision making course. And what we want here is that stuff that is connected, even if it's like an audio for that was spoken in the first minute, but we have a very good image that connects to it in minute 55, right? We want to find this, and we want to say, hey, this is a positive pair. This is something that doesn't have a lot of distance, and this is where we want to minimize. And if we zoom in now, let's focus on the positive pairs here. This would represent a scenario where system 1 thinking matches with an appropriate visual. So imagine an audio clip saying, this seems familiar, let's go with it, paired with a familiar visual like a photo of a casual meeting room. And this alignment of the audio and this alignment between the audio and the simple image helps the model to learn that these data points do belong together. Contrastively, right, we also focus on negative pairs. So if you look at the bottom part of the chart, here the audio clip might say, let's consider all factors carefully, paired with a complex visual like a detailed data chart. You know, when we have this slow, thoughtful tone of the audio, and we have a lot of stuff, you know, in the image, this might not connect so well. But these are just dummy images. So the goal here is that stuff that's similar goes together, stuff that's not similar, very, very far away. And in the end, how does this actually improve our multimodal systems? So by training the model with these pairs, contrastive learning helps the AI make and learn the nuanced relationships between the audio and the visual. And this training allows the model to generate more accurate and relevant responses when working with multimodal data, such as. Therefore, we can definitely say that contrastive learning enhances multimodal systems. Therefore, we can definitely say that contrastive learning enhances multimodal systems. How? Because we allow the AI to learn the nuanced relationships between the audio and the visual data. And this training allows the model to generate more accurate and relevant responses when working with multimodal data. Therefore, let's take now one step back and focus on the broader applications of multimodal applications. So beyond our decision-making course, contrastive learning enhances performance across various applications. So for instance, consider aligning customer service dialogues with facial expressions for improved communication, or synchronizing video content with background audio to create immersive experiences. So this technique is absolutely invaluable for integrating different data types seamlessly. To sum it up, contrastive learning helps models better understand and integrate multimodal data. In our example, using decision-making styles with audio and images, the model learns to minimize and maximize distances between similar and dissimilar pairs. As a final thought, it's very important that we understand contrastive learning. So this is something that it is intuitive. So we have different data points, we find those that are similar. The question is really more about the how. And this is what we need to think about. One way that we'll use is the clip model, but that is just in the next video. I'll see you then. Welcome back. In this video, we're going to cover the clip model. Clip model was developed by OpenAI and stands for Contrastive Language Image Pre-training, and is designed to understand and relate images and text without needing traditional task-specific fine-tuning. And this ability makes it very versatile, especially in applications like zero-shot image classification, where it can recognize objects in images it has never seen before, just by understanding the text description. Let's have a look at an overview of clip. So let's begin with the foundation of the clip model, which is the contrastive pre-training. So take a look at this image. The clip model learns by training on a large data set of images and their corresponding text description. The key here is how it learns to associate a given image with its correct text description while differentiating it from incorrect ones. This process is what we call contrastive learning. In the diagram, we see two encoders, one for text and one for images. The text encoder processes a phrase like pepper the housey pop, converting it to a text embedding. Similarly, the image encoder processes a corresponding image, in this case a picture of a puppy, and generates an image embedding. The clip model then tries to align these embeddings for correct pairs, like the phrase pepper the Aussie pop and the actual image of the puppy, while pushing apart embeddings for incorrect pairs. This alignment process allows Clip to effectively match text to images and vice versa. Therefore, as a key idea, Clip matches text with images, and this is one way of doing contrastive learning, and we don't need to do fine-tuning of models. This is something that's going to be very, very easy. Next, we move to how Clip can create dataset classifier. And this can be done from label text alone. Imagine that we have a dataset with different categories like plane, car, dog, bird. Traditionally, you need to fine-tune a model specifically for this dataset. However, with Clip, we don't. As shown in the second image, you input a label like photo of a dog into the text encoder. This text description is converted into an embedding that represents what the dog looks like conceptually. The model then compares this text embedding with the embeddings of all images in the dataset. The image that best aligns with the text description is identified as belonging to the corresponding category. Therefore, and before we continue, as a key idea, Clip allows you to create a classifier by simply describing the categories in natural language, bypassing the need for traditional task-specific training. Therefore, we now move to zero-shot prediction. So one of the most impressive capabilities of Clip is the zero-shot prediction. This means that Clip can recognize objects and classify images it has not seen before. In this image here, we can see an example where an unseen image of a dog is processed by the image encoder. The resulting image embedding is then compared with a set of text embeddings created from the descriptions like photo of a plane, photo of a car, etc. The model identifies the best match, in this case recognizing the image as a photo of a dog, without ever having been explicitly trained on that specific image. And this is a very important part here for Clip, because we don't need to train and we can immediately predict. To sum it up, right? So Clip works by learning powerful representations of both text and images through contrastive learning. The diagrams that we have explored show how Clip leverages these capabilities in real-world applications, making it very versatile. And its ability to perform zero-shot predictions is particularly noteworthy as it opens up possibilities for AI to interact with and understand the world in a more flexible, human-like way. When it comes to the future, like the applications are vast, from enhancing search engines to creating more intuitive AI systems. Clip does set the stage. And as we continue to explore this model, think about all the ways that you could use it and all the very cool apps and systems that you could build. Side note, Clip is open sourced, so this is also a very cool thing. This is it. Until the next video, have fun. Welcome back. In this video, we'll start a journey to embed our audio. It's easier for images to embed them. For the audio, it's a bit more tricky. At the same time, we're going to do all the setup for both audio and images when it comes to the embeddings. Here we go. As you know already, we're going to use the Clip model for all of this. So import libraries. We're going to, from transformers, and we're going to import the Clip processor, the Clip model, and the Clip tokenizer. Here we go. Import torch, absolutely. And then from NumPy, or sorry about that. Import numpy as np. Shift enter. Then what we do is that we load the model processor and tokenizer. Here we go. Start with the model. I'm going to do it once, and then it's fairly straightforward. From clip model, from pre-trained, and then OpenAI, and then clip with base, and then patch 32. And here you go. And we have everything. Let me do Control Enter and clip model API. Actually, I don't want the block. I want the GitHub. Alternatively, you can use the clip directly from OpenAI. Personally, I would not recommend. That is because this is something that's not, how can I put it? It's not really updated. And therefore, because most of the libraries that we use, they work with some other libraries. And with the exception of, 1 to 2 months ago, but all of this is old. And that is because this is actually open source. So you can actually go and check their model, how it works. If you're interested in it, you can modify it, you can make it your own. This is open source. And therefore, as they don't make money out of this is a bit outdated. But it is available in Transformers. And Transformers is a library that is always, or at least until now, it's up to date, and they're working on it. And it's easier to integrate stuff. Now, we would have our, we would get the transcribed text. Here we go. So this was our transcription dot text, if you recall. Or no, what was the name? Transcript dot text. Transcript dot text. Now, in case that you took a break and you want to get it, it will be with open transcript path read as file, and then okay, let me call it transcript. Transcript text would be equals to file dot read. But we have it, so no need to do this. Or better yet, let me do it. Let me do it like this. We open it, I save it, I have my transcript underscore text. And then the last thing I want to do is to tokenize the entire text. So tokens equals to our tokenizer. We include our transcript underscore text. Return tensors equals to pt for PyTorch. Okay, you know what will happen. And then padding equals to true. Here we go. If we have a quick preview at our tokens, we get an error. Text input must be of type str, batch or single pre-tokenized example. Okay. So let me have a look at my transcript underscore text. Okay, so this I did. There we go. I'm missing the parentheses here. And then if I get my transcript, here we go. All good, all good. So I'm tokenizing this. We have it here. Then what we do is that we just get input IDs, or let me show it to you before I store it. And then we have a double list. So we have 0. And this way we just have the tensor tokens equals to this. Then it's always good. So we would print with an F string the number of tokens is, and then length of tokens. And let me do Control Enter, and here you go. So you should also get something. If it's not this, it should be very, very similar to this. Now we need to chunk this, and why? So the clip model requires 77 tokens per chunk. And what we have currently, we have one chunk of 9,862. And we're going to do this. We have done this before, right? So we have done this in the multimodal, but we're going to use something different for this. That is because I want to always or just use the transformer library, because that's the thing that's least expected to give me an error in the future. So that is the reason. And therefore, for this to be up to date all the time, I'm not going to mix LangChain with the transformers. That's the main reason. You could try, it would work, but it's something that you need to be more careful. It's not a big difference, but it just means that we need to code this because we don't have a specific function, as far as I know, with transformers. I'll see you in the next video. Welcome back. Now let's go to the next step, which is to create chunks for our tokens. So our max tokens is 77. And then we'll have this, what I'm going to call transcription chunks. And this is empty. And what I'm going to do, this is a loop that's basically going to, okay, we're going to put 77, we reach 77, we go to the next one, 77, so on and so on. So that in the end, we are going to basically have 9,862 divided by 77 chunks, plus whatever is the remainder. For I in range, and this is 0, to the length of tokens, this is 9,862 intervals of max tokens. And let me add here an n and colon. So my chunk is, I go to my tokens and I go from I to I plus max token. So I get, and let me explain it. So for instance, in the first one, I start with 0 and I go from 0 to 0 plus 77. So from 0 to 77. Then I go to the next one, which would then be 78. Then it will be, okay, 78. And then up to 78 plus 77 and so on. And we get the chunks, and then our transcription chunks, I will append each chunk. Let's add a print here. So with an F string, yeah, okay. The number of chunks is and then length of transcription chunks. Here we go. Let me do Control Enter. We have 129. If I do, what was it? 9862 divided by 77. This should be 128 something. And then the something is the remainder, which is the last chunk. And this then actually leads to the next step, which is our text embeddings. So this means that we embed the tokens in each chunk. Text embeddings equals to this list. And then what I do is that I go to each chunk. I'm going to then unsqueeze. So this is what it is called, but let me do it step by step. So if I get here, so my transcription chunks, let me get it here. Here we go. If I get number 0, right? So next step is that, for instance, I would then do dot unsqueeze. Okay, unsqueeze with a 0 there. And so basically this moves back 1, and I would store it under inputs. Inputs equals to, this would be a dictionary, so input IDs, colon, and then our transcription chunk. I need to close the dictionary. This is, in a sense, moving one step back. Whereas before, where was it? Let me see. Here we go. We had this 0 here. So this is basically, adding one extra step. We have a look here at our inputs. And this is our inputs, input IDs, and here we have them. And then what we do is with torch and then no grad. And this no grad here doesn't have a lot of impact, but it saves on computation. So it's a very standard practice. We would have the text embedding. Text embeddings. And then equals to, I use the model, get text features. And it's this get text features that leads to the clip model that will enable us to actually do this contrastive learning. And like this, inputs, let's inspect. So text embeddings. Here we go. Control Enter. Oopsie. And here you go. So these are all the features from that we get, and these are our text embeddings. And what we do next is that we flatten everything. Let's have a look. So what happens next? We have our text embeddings. We're going to append my text embeddings, text embedding, or better yet, so text embeddings, plural, and this should be singular. We have our text embedding, we use the CPU. We don't need to use anything else. We transform to NumPy. And then we flatten everything, parentheses. Let's have a look. So at our text embeddings, Control Enter. And so tensor object has no attribute. Yeah, of course. Because here I'm appending to my empty list. Let me do Control Enter once more. And here we have it, right? So now we have this array. And this is what enables us to then, we'll compare everything that is in this text embedding. So these are the numerical representations of our data. And we're going to compare these embeddings from the text to the embeddings that are in the images. Therefore, I need to wrap this up. We're going to call it text embedding numpy. And then I transform this to a numpy array. And here we go. If we have a quick preview at our text embedding numpy, Control Enter. Here we go. So this is the correct format. It's a double list, an array. But the important thing is this dot shape. Right? So this is one with 512 embeddings. And all of this must have 512 embeddings. It's part of the clip model. And all of them will have. So what we do next is that we make sure that all of this is working. And here we go. So this text embedding, so this part here will remain outside, but this part here will go inside the loop. So for chunk in transcription chunks, let me give it some space here. Here we ensure the chunk is in the correct shape, and this requires the input IDs, the double list, and then here we would then get the text embedding. Let me show that everything is correct. So we have the inputs, we include the inputs, we get the text features based on our clip model, and we store them as text embedding. We then append our text embeddings that we have transformed into a numpy, and we have flattened everything. Then, last step here. So we convert the list of embeddings to a numpy array. Here we go. And we can then, print the shape. And here you go. So with a print with an F string text embedding shape is text embedding shape, and then the bottom part I don't need. Here you go. Control Enter. And then, of course, we would get 129, which is the number of chunks, right? And we would have 512 embeddings for each. And this is step one. We have all of our chunks, each with their own embeddings. And now we go to the images. We get the embeddings for the images. And then what we do in the end is that we compare. We see which ones are the most similar. And that is the end goal. This is still running. It has stopped, as you can see, right? So 129 by 512. I'm going to stop this video here. Next one, we need now to embed the images. I'll see you then. Welcome back. Let's go to our step number 7, which is for embedding the images. I'll recall that an embedding is a numerical representation of the data. So from PIL, which is this library for images, I would import image. And here you go. I need here. Let me see if I've defined it. Here you go. It's output folder. let me define it again differently. Here, what I want to do is embed the images. So the frames folder, this one is called frames. Here you go. Let me see the transcripts. Here you go. Here it is. Frames. And then we are going to store the image embeddings and store here the image paths that we are going to use. So this is something that will be helpful as you create some images or some data visualization and we want to get the images. This will be important. So for frame file in OS list dir for directory, and we get the frames folder, and should be list dir, all in the same. So frames folder, parenthesis, colon, and here you go. So we want just to get the things that end with PNG. Let's have a quick look at our frames. PNG, PNG, PNG. You can see that most of the images is me in a not so photogenic way. But yeah, it's really not photogenic. But we are going to get everything that ends with a PNG. So if frame file ends with and then dot PNG, here we go. Our frame path os dot path dot join. We have the frames folder and the frame file, and then we append the frame path. So this is how we store it. And we continue. We then load and pre-process the image. How we do it? First, image equals, we have our image, we open based on the frame path. And then what we do next is that we store it under these inputs that we use the processor. What is this processor? It's this one that is this clip processor. And this is going to pre-process. So images equals to image. And here we go. Okay, this is one parenthesis too many. And then return tensors equals to PyTorch. And then we generate the image embedding. I see an error. Let's fix processor. And here I have processor. I wonder if something is wrong. Let me see if we can get processor is not defined. Okay, weird. When we get there, we get there. Like no real reason to worry too much about it. With torch and then no gradient. Image embedding model, get image features. This is very similar to what we did here. We're going to get something with 512. We have the inputs, and then we have our image embeddings that we have here. We're going to append the image embedding, and then is the same dance. CPU dot numpy dot flatten image embeddings numpy, convert to a numpy array. And we use this numpy array just in case, because the last command here is flatten. So always have this, or always triple check. Always add something in the end that makes sure that the output is what you want. In this case, a numpy array. Let's do Control Enter and let's see what's happening with this processor. So name processor is not defined, but this is weird. Okay, let me do Control Enter here once more. Processor, and it has run. Okay, there was something different, right? Ah, okay, I had 3 S's. If you caught it, well done. Let me do Control Enter once more. And we should have, I don't know how many frames we had. Did we? Oopsie, let's have a look. Okay, it's quite a bit of frames. So 372 frames, right? Because so the 0 doesn't count, right? Because we start at 0, 0, 0, and then 1, 0. So 372. But let's confirm this when we're done. Now let's learn a bit about contrastive learning. Again, to reinforce how this works, because this can be confusing. Because we are doing a lot of coding, and I fear that sometimes, because the coding can be complex, that this makes the concepts more complex than what it should be. But in general, what happens is that we have these text embeddings, which have this features and these numerical representations of our data. And we have this for the text, and we have this for the images. And then what we're going to do now is, let's get these features from one, let's get these features from another. And for instance, let's take from the chunk text 1, right? Let's see which is the most similar from all of our 372 frames. Let's see which one is the most similar, and let's rank them all. And this is what we want to do. We want to have the most relevant chunk with the most relevant image, or even the most relevant chunk with, the top 3, top 5 images. This is what we want to do, so that we are matching all of our data. And this is the heart of contrastive learning. So far, it has been complex. From now on, it will be a bit simpler. But yeah, I don't want to overpromise. I'll see you in the next video. Or better yet, before I see you in the next video, we're done at 373. 373? Okay. Okay, stupid. Missing the first one. Index starts at 0. Or in this case, seconds start at 0. So 373. This is it. I'll see you in the next video. Welcome back. Let's discuss cosine similarity. This is a fundamental tool in data science and machine learning that helps us measure how similar two objects are. So whether you're comparing text documents, images, even audio files, cosine similarity is powerful and intuitive for understanding relationships between different types of data. And by the end of this video, you'll understand what cosine similarity is and also how to apply it. Let's focus first on the core idea. So let's start with this basic idea. Cosine similarity measures the cosine of the angle between two vectors in a multi-dimensional space. Imagine these vectors as arrows pointing from the origin of a graph to a different points. The closer the vectors are, then the smaller the angle between them, and the more similar they are. Conversely, if the vectors point in very different directions, the angle is very large, and the cosine similarity is low. Looking at it intuitively, if two objects are similar, they point in the same direction. Cosine similarity captures this by focusing on the direction rather than the magnitude of the vectors. Let's visualize this a bit better. So imagine that we have two arrows on a piece of paper. If these arrows are almost on top of each other, the angle between them is very small. This will result in the cosine similarity close to 1, which means that they are very similar. Now, if the arrows point in opposite directions, the angle between them is large, making the cosine similarity close to -1, indicating that they are dissimilar. If the arrows are perpendicular, so 90 degrees, cosine similarity will be 0, indicating no similarity at all. Therefore, as a key idea, the cosine similarity focuses on direction. When vectors, representing, for instance, text documents or image features are aligned, their cosine similarity is high, meaning that they share similar characteristics. If we look at the mathematical formula, this is calculated as A times B. So A times B is a dot product of the vectors and of their corresponding elements, and then A and B. So these represent the magnitudes, so lengths of vectors. This is so that they're absolute. I think that's the correct word in English, when we have two lines. And then the result is a value between -1 and 1, where 1 indicates, the same, so identical direction. 0 is orthogonality, no similarity, and -1 indicates opposite direction. If we look at a practical example with text documents, let's say that we have two of them. One is a job description for a data scientist, and the other one is a resume. We can represent each document as a vector where each dimension corresponds to a specific word, and the value in that dimension is the frequency of the word in the document. As an example, so we have here document A, job description, data science, machine learning, Python statistics. Document B, which will be the resume, will have Python statistics, machine learning, deep learning. We create vectors from these documents by counting the frequency of each word. Next, we compute the cosine similarity between these vectors. If it's high, indicates that the resume is a good match for the job description because the key terms align closely. Therefore, as a key idea, cosine similarity helps compare documents, focusing on the presence and frequency of shared words. And this makes it easier to find the best match. If we apply it to images, so this isn't just for text, so imagine that we have two cats. You can represent each image as a vector of pixel values or as a set of features extracted by the model, like clip. And we calculate the cosine similarity. So for instance, image A, a vector representing the image of a cat sitting on a sofa. Image B, a vector representing the image of a cat lying on a bed. And if these vectors have a high cosine similarity, it means that the images are visually similar. Perhaps because the cats are in similar poses or the backgrounds are alike. Now let's cover real-world applications. Here we would have search engines. When you type a query into a search engine, cosine similarity helps match your query with the most relevant documents or web pages. Recommendation systems. So think Netflix, Amazon, they use it to recommend movies or products. And image recognition, so in facial recognition systems, cosine similarity is used to match a person's face with images in the database. Now let's conclude here. So to wrap up, cosine similarity is very powerful for comparing things. So we cover here text with text, image with image, but as we'll see, we'll do text with image. And by measuring the angle between vectors, it gives us a sense of how similar they are, focusing on the direction rather than the magnitude. This makes it especially useful in applications like text analysis, image recognition, etc. And cosine similarity opens the door for more intuitive and effective ways of comparing data, as we'll be able to see. It's also very, very easy to apply, which is the best one. Now, as a last thing, so I've covered this with simple examples and simple angles, but if you think about it, like our embeddings are massive. Therefore, this is a multi-dimensional stuff. So it's very difficult. It's impossible for us. We can do 3 dimensions. This is multi-dimensional stuff. And therefore, visualizing how this works it's a bit impossible for us. But the general idea is that we use cosine similarity to see how similar are our embeddings. Until the next video, have fun. Welcome back. In this video, we're now going to, in a sense, it's like the most important video because it's when we bring everything together. As I've tried to share a lot of times, the most difficult thing about the RAG is not the retrieval, it's not even the generation, it's really the pre-processing. Because, for instance, in this case, we have 10 steps. Step 1 to 8 is preparing. Step 9 is retrieval. Step 10 is generation. Spoiler alert. So I'm going to call this one contrastive learning. Try to explore. I really want this to be extremely intuitive in a way that it works. So from sklearn dot metrics dot pairwise import cosine similarity, and then import matplotlib dot pyplot splt and import random. This is going to be for some visualization. And matplotlib with 1b, and here we go. So calculate the cosine similarity matrix. And this is like we have done so much coding, but this is very, very easy. So similarities equals to, we use this cosine similarity. And then inside, I include my text embedding numpy, and then my image embedding numpy. And if we have a quick preview here, so similarities, shift enter. So this is it. Now, might not tell you much, but each of this represents the similarities. And what we want to see is, okay, check the shape of the similarities. And what do you expect, right? So what one would expect to see here? Let's think about it, right? So intuitively, we have 100, okay, I'm forgetting the number. We have 129 text embeddings. No, we have 129 chunks, and we have 373 frames. So with the similarities, we expect something that is 129 by 773. And for each of these pairs, right, we have a degree of similarity. And this is what we have exactly. So for instance, so print, and with an F string, yeah, the shape of similarities is similarities.shape 129 by 773. And you can see that they don't change much currently, which makes sense. All of them are about decision making. You can see that a lot of them, or I don't know if you had the time to have a look, but like they follow a similar color pattern, right? So white screen, so on. There's like a lot of the same things that have a similar level of information. Next up, so that I show it to you. So for instance, if we want to retrieve the top, K similar images for each text chunk, right? So for instance, it would be, top K. Let's say we want to retrieve the top 5. And we just want to have a quick view, right? So nothing too much. So for I, and then text chunk in enumerate similarities. Here you go. What I do is that I get the similar indices. And how this works is that I go to each text chunk, and then I'm going to arg sort parentheses. I'm going to get the minus top k, so the bottom, or the top 5. Here we go. And then here, starting from the last one, and then print with an f string, f, and then top k, images for each chunk I, and then I also extract the similar indices. Here we go. So something very straightforward. I got tiny error. Here you go. Guess I'm missing some parentheses here. Let's try again. And here you go. So this is how it works. So for instance, we have that for chunk 1. This is not correct, right? You cannot have the same images. So for I, text chunk in enumerate similarities, and then square brackets here, minus top k with a colon, and then colon, minus 1. So but here something is weird because all of them, they have the same level. So I think the problem runs deeper. So we need to understand and have some kind of debugging. So I want to inspect the image embedding NumPy. Let's have a quick preview. So minus 22, minus 33, minus 21. So all of this, they look different. Therefore, the next step, I want to inspect the text embedding NumPy. So text embedding NumPy. Hopefully, it will come from here. It comes from here. They're all the same. Good to know. Therefore, let's take one step back. The issue comes from here, but then we can also triple check here inspect the transcription chunks to make sure that the issue is here and not above. So inspect the transcription chunks, and then transcription chunks. It's quite significant. So 49406, 269. Okay, it doesn't seem to be here. So text embeddings for chunk in transcription chunks, inputs. And let me compare this with my notes. And where was it? Here we go. So input IDs, transcription chunks. Okay, yeah. I think that I see, because I'm always doing the same. And basically, I don't really have a loop here. So mea culpa here. This was my problem, but now it's fixed. And I should Control Enter. And then let's inspect the text embeddings NumPy. Might as well, I'm going to write to myself. And this was in the chunking and embedding text. I'm going to add myself a note. Add a note that I made a mistake in the embedding. So that I add this as a lecture. Okay, so we have our new text embeddings NumPy. This means that we can do our similarities once more. Now they all seem different. Very good. And this could remain the same. And now we have the top 5 images for each chunk, and all of them are different. And you can for sure have a look and still, potentially even inspect this a bit more. But I'm going to stop this video now. I've done what I wanted. I've debugged as well, which was not planned, but often necessary. I'll see you in the next video. Welcome back. Now that we have done contrastive learning, we're now going to the next step. But before we get to it, I want us to visualize. So we have done a first level of, it's not really a visualization, but we can see the frames for each of the chunks. And now what I want to do is that I want to set up a code snippet that takes 5 random images, and then we visualize the chunks of text that are attached to it. Or alternatively, and this is what we're going to do, we're going to take 5 random text, and then we are going to visualize the 3 most similar images. Let's get started. And this is why we have the random. So set a random seed for reproducibility. So random.seed and then 1502. This is my standard one. Select 5 random text chunk indices. And then, so random text indices equals to, use random again. We sample. And then what we do is that we range the length of text embeddings M and P. So comma there, and we get 5. So 5 is more than enough to visualize. And I actually wanted that. So print random text chunk indices. So you should have this. So if you have the same level of images, texts, and so on, this should be your output. And then what we do is that we find the 3 most similar images for each text. And this is very similar to this, right? Because here we went and we get, or better yet, we got the 5 most, relevant images. Here we get 3. So here we go. So what we do is, so text to images similarities equals to, here we go, for index in random text image indices. Here we go. This is all correct, but so similar images equals to, similar images. This should be okay. We go to similarities. We go to that specific index, and then we sort what we do. Then we get the top 3. So -3, 2. And then we go to the right, and then we need to invert everything. This is how this works. And then we have our text, 2 images, similarities, we append our similar images. Shift Enter. And now we actually do our data visualization of the text and images. And so for I, and then text index in, we enumerate our random text images. So we go through each of them. So plt.figure, figure, this should be big size equals to 10.8. This is usually good. We start by displaying the text chunk, and with a print f-string text chunk. So text chunk, curly brackets, and then here we have I plus 1. Here we go. And then here, what we do is that we use this, and then we join, right? So we join, but then have in mind, right? What we have currently are text chunk indices. And at the same time, what we have is tokens. So we need to, take a step back. So join, and here you go. So join parentheses, and let me start here with a list. Tokenizer is going to decode, and here we include token, and then here for token in transcription chunks, and then here at the very end, I'm going to include my text index. Let's see if this works. So I immediately see here an error. So let's understand what is happening. So we have an F string, and this F string is potentially having, so should be a parenthesis, some quotes to close, and then curly brackets, and then a parenthesis. And here we go. I think potentially okay, so now that I look at the colors, right? This is red, this is not red. So let me bring this back. So this should be in the sim line. Alternative, I should be able to do this, right? Let's try like this. Here we go. So this works. And so we have this step, and we know that this is working. I have here the figure size, so 5 of them, and these are the 5 random text chunks. Then, after I have this, I can then display the similar images, but of course I want it together with the text. So hopefully this works. So for J, and then image index, so IDX, in enumerate, and then, so we go to our text, 2 images similarities, and here this is access through the I. We have that we start by opening the image, so image equals to our image dot open, and then we go to our image paths, and then we get the image IDX, and then PLT subplot. So 1, okay, let me get there, 3, J plus 1, right? So, because we have 3, right? Exactly. So here should be 3, 1 to 3, and then we have 1, 2, 3. And then we would have PLT, show images, axis off. And then let's add PLT title. And then we have the F image J plus 1. Let's do Control Enter, see if this works. And here you go. So not perfect. And I don't 100% understand why. Oh, I see. No, I don't see. Because like I have the loop, right? But at the same time, I would like to have the text chunk, then the images. And this is not really happening. So it's not 100% clear why this is occurring. So if you think about it, right? So we start with a loop. We have the figure size. We display the text, and then we go to the image. And this should all be done in one go. So we should have one print, one display, and then return, because this should be the order. I wonder, so the PLT dot, potentially I'm missing these parentheses. And here we go. It was exactly this. So we have, for instance, text chunk 1, which is powerful, and it can infer with system 2 thinking, even if we consciously try to focus on something else. The Stroop effect can be extremely important when making presentations, as it highlights the influence of non-verbal cues and the way information is presented to process information accurately. For example, imagine you're making a presentation to a group of stakeholders, and then, so this, for instance, it has some keywords like presentation, so on. So there's like quite a few of, how to put it, some frames here in the images. So we immediately get those. It's a way, right? So, and this is what I wanted to show to you in the end. And this is how our clip model, together with our cosine similarities, is in the end merging our text with our images. I'm going to stop here. I hope you enjoyed this video, and next time we're going to go to our next step, because we're done with step 8, so now it's step 9, the retrieval system. I'll see you in the next video. Welcome back. Let's start with our step number 9, which is our retrieval system. And we have done this so often that you know all the steps by heart. We start with, let's define a query. So for instance, query would be which cognitive biases are discussed. Here you go. So this is one. We start by tokenizing the query. Here we go. And then here, so query tokens. Here we have this tokenizer. Query. Here, return sensors equals to PT. Padding equals to true. And then, so we would just get here our input IDs. Query tokens, finding error. Padding equals to true, because here should be a comma, not a dot. Here we go. Return sensors equals to PyTorch. Why is this not recognized? Did I do something wrong? Return tensors. Here we go. So this is done. And then we are going to generate the query embeddings in the joint embedding space. What does this mean? We use the clip model. So now we're going to find the most similar text features, and then we're going to compare it to what we had. So with torch no grad, here we go, query embedding equals model get text features, here we go, parentheses, and then input IDs equals our query tokens, and then we have this part here, and then we do what we've done before, CPU dot numpy dot flatten. Here we go. Let's print with an f string the shape of the query embedding is query embedding shape. Get a tiny error. Let's fix this. Get text features. Got an expected keyword argument. Input INS, so it should be IDs. And here you go. So 512. Because again, it's just one query, right? So we have one query, should have 512 embeddings. Very quick video, but I'm going to stop here. This was the tokenization part, and now what we do is this kind of search. And this search is a bit different because we use the cosine similarity to find the most similar. Process is the same. We're always trying to find what is the most similar here when it comes to the retrieval. In this case, since we have worked so much with the cosine similarity, now we find what kind of text embeddings are most similar to our query embeddings. I'll see you in the next video. Welcome back. In this video, we are going to first compute the cosine similarity between the query and the transcripts. Here we go. So cosine similarity, and then this one equals to our cosine similarity. Here we are going to include our query embedding. Need to do it here inside the list. And we include our text embedding NP. Here you go. And here we include a 0. So with that, we just decrease the number of lists. And so here we add a list to our query embedding, and then so that has the same number of square brackets, and then we remove cosine similarity. We can have a quick preview, and here, so immediately pops here this 75 here. We also see some 50s, 60 here. So there is 78 at the very end. So there is definitely some level of similarity. Therefore, now what we need, so we need to define how many chunks we want. And so top, okay, text equals to, let's say that we retrieve 10. And then we retrieve the indices of the top top k most similar text chunks. Here we go. So top k text indices equals to, we go to our text similarities, and then we do arc sort, and then we get the top k texts. We make sure everything is ordered, and we can have a quick preview. Text similarities is not defined. Why is that? Okay, I called it cosine. Let me change here. Actually, is it the same name? This could be an issue. Similarities. Okay, it's not the same name. Let me change here to text similarities. And here, text similarities. I like that the names have some degree, or that tells me exactly what I should look for. Okay, why is this happening? Let me run. So query tokens, query embedding, enter. Object is not callable. Let me come, because I just changed the name that I stored, so it's super, super odd. Let me go back to the audio. Get here our text embedding NumPy. And then go back here. So text similarities is the cosine similarity, query embedding, text embedding pi. And while this is running, I come back here. Actually, this was about it for this point. So let me pause here. While I look, okay, so it's not an issue. Let me have here explain error. And you know what I think? Hey, okay, the thing is, I called it the name. It was the same one, right? So this potentially means that I need to import this again. Here we go. Let's try now. See if this works. Here you go. So rule number 1, never call something the name of a function. Okay. Then let's have a look at the top k text indices. So we would look at 1 to 8, 79, 0, 37, 92. And then now what we do is that we retrieve the images. And you have two options. And you either repeat the same, but if you repeat the same and you find the cosine similarity between the query and the image, why are we doing contrastive learning? Like, there's no point. We could just put everything under the same database, very similar to our unstructured data that we did in the previous section, and, just go at it. The point here is that now we compare text to text, and then since we already have the images, then we retrieve the images that are connected to our text. So it's query text image. Therefore, retrieve the closest images for each text chunk. I'll leave it to you. I'm going to pick one. I think one is more than enough. Top k images indices equals to this, and then for IDX in top k text indices, similar images equals to our similarities, IDX arg sort minus top, and then k text, something like that. We look at the 10. Here we go. And then our top K images indices, we append the similar images. Finally, this is an important point. We remove any duplicates and limit to the top K images. So let's start here, or better yet, let me show it to you. So list, we would set top K images indices. There you go. Let me do Control Enter. And hashable type, top K images indices. Question is why? Do I need to include up to top K text? Control Enter. So the issue remains the same. And here you go. So we go to our similarities, IDX, arcsort. We look through the top K text. And let me also triple check when we did this. We selected 5. Here we selected the top 3. So here I actually don't want top K text. I want -1. And here you go. This I should not need, but this numpy dot n the array, this is odd because it's this part. So top K, because this should be a list, right? Because it is a list. Top K images indices. I'm seeing something. And here we go. I'm actually having here some kind of I'm trying to understand what is this. So set items for sublist in top K indices for item in sublist up to X. And let's have a quick preview, see what is here. And here we have it. In case that we were to include 2, this would be what we would. And let's say that we would include here a number of images per chunk, or images per chunk. It's tinier. Let's do 2. Control C, and then minus this. So this is better. And this leads to actually how many do we have? So we print the top K indices. No, I actually want the total images are length. This, we have 18. So from 10, 2 of them should have had duplicates, so they were removed. And that is it. So I'm going to stop here. We have now done the complete retrieval. And let me just do a quick recap here, because I think there were some moments where it was not flowing as much as I would have liked. We have the query. We have the query tokens. We use the query tokens to get the embeddings. We compare the embeddings with the text embedding. And then we have a look at what are the most relevant texts or chunks to our query. In this case, it's this Then we get the images. I said, let's do 2 per chunk. And then we remove duplicates. We get to 18. This is it. And I'll see you in the next video. Welcome back. We now can go to step 10, which is our generation system. And it's very exciting that we got here. So let's do it. We need to import base 64 because this is a format that is required for our GPT-4 to read our images. We start by combining the retrieved text chunks. So retrieved text is this, and then for IDX, let's do it. Top K text indices, retrieve text, dot append, tokenizer, decode, transcription, chunks, IDX, and then retrieve text. I would just join everything. Let's have a quick preview here. So at our retrieved text and see how it works. So you can see that everything here is together. We also have indicators for end of text, start of text. Then we also want to convert the images and append them. Here you go. So base 64 frames. It's an empty list. So for IDX in top K images indices. Here we go. So we start here. Okay, this is very different than what I have. Okay, I'm going to follow mine. So we start with opening the path. So image, path, and then this is the image, paths, IDX. Not saying it was different. I was just saying it's, or better yet, I'm not saying it was wrong, but it is different. And personally, I like mine, which is more step by step. It enables me to also explain better to you. So we open the image, and this is set as read binary, then as image file. And then what I do is that this base 64 image, I use the base 64 to be 64 encode image file read to decode UTF-8. And okay, append base 64 and then image. Here we go. Let's have a image again. Okay, here we go. Let's have now a quick base 64 frames. Okay, I'm going to get an error. Base 64 frames, so that we always see what we get out of it. In the meantime, we can define the model and system prompt. So model equals the GPT and then 4.0 mini system prompt. And okay, my system froze. Okay, here we go. We should have all 18 images over here. And so hide system prompt. Let's go. So you are an expert teacher that summarizes, visual and transcribe content. Something like this. Doesn't need to be extremely serious here. And that is it. So I'm going to stop here. I'll return in the next video where we'll also wrap up. So very excited about this. It's been a long journey. Hope you enjoyed it. I'll see you in the next video. Welcome back. Now we need to prepare the user message content. So user message content here. This is a list. Here we go. So these are the frames from the video, and comma, and then we are going to map, so lambda, and then here x, so type here with lowercase t, colon, image URL, go to the right, comma, and then our image URL. This is a dictionary, and this is a URL, colon, f-string, data, colon, image. I actually wonder, not gotten any shortcut in a while. JPEG, and then semicolon, base 64. Here we go, comma. We include here an X, and here you go, comma, and then detail here, colon, and then here, yeah, should include high, for instance. Go here, and then base 64, and here you go, so base 64 frames. So let me do Shift Enter, and expected after dictionary key, so image URL, colon, try again. Here you go. This appears to be working, though. Okay, there was like this squiggly line, sounded like an error, but it wasn't. Now let's wrap it up. Call the OpenAI API to generate a summary. Here we go. We have our response client. Yeah, let's client chat completions create model equals model, messages role system content system prompt. Here we go, curly brackets, comma, and then role user content, not the retrieved text, but our user message content. And okay, now I was just having a look at it because it was feeling weird and I could not explain why, but we're missing the retrieved text, and this one is here. So let me just triple check with my notes. Yeah, absolutely. So comma here, and then we start here. So type here is text, and then the text here comes from our retrieved text. So retrieved text, let me confirm, absolutely. So Control Enter. We have our user message content, comma here, close this, comma, temperature, I don't know, set to 0.3. Again, I don't appreciate creativity most of the times. Let me do Control Enter. See if this works. And then we would, generate the response. Generated response choices 0 message content. And then we just print the generated response. So nothing too fancy. We just focused here on making our gen part work. Here we go. So the video frames present various concepts related to decision-making, biases and their implications, mutual causality bias, hypothesis, obesity and decision-making. Okay, this was not good. Gambling and risk, system 1 and system 2 thinking, loss aversion, narrow framing, anchoring bias, happiness and satisfaction, diverse information sources. Okay, this is like half correct. So there's a few things here that I discussed, but obviously highlights the prevalence of obesity. I don't do this, for instance, not at all. So also the gambling and risk, I don't do this. And there could be many reasons for this. So one flaw for me is the chunking. So 77 is not that much, especially because here in our query, and at least in this topic, this is something that I would explain a topic for several minutes. Therefore, the chunks could be bigger. So this is one clear flaw here that we have currently. And as well, the fact that this is still not something that's easy. You saw how it was with unstructured data, right? It was simple, it was straightforward. This was neither simple nor straightforward. So there's a lot of work here. I do expect to remake this section quite soon, because I do expect improvements. So if you do have an improvement, if you found something, let me know. Very eager to improve this section here. That's it. I'm going to stop here. I had fun. I hope that you also had fun, and I'll see you in the next video. You have made it to the end of our multimodal RAG adventure. So let's take a moment to celebrate what you have accomplished and reflect on the exciting skills that you have picked up along the way. So we explored multimodal RAG like never before. You dove into it, you learned how to combine different types of data into a single powerful AI system. And by doing this, you've unlocked the ability to create models that can understand and generate content just like humans do across various media. We got our hands dirty. So you rolled up your sleeves to set up our Python and do some programming. You learned how to extract audio, compress it, prepare it for analysis. These are essential skills. We mastered the Whisper model for audio transcription. You tackled it. So whether it's transcribing a podcast or extracting valuable insights from video content, you've got the skills to handle it all. This was a big win for working with spoken language and a major step towards integrating audio into our models. We aligned images with clip and contrastive learning. You learn how to create embeddings for images and text and match them up with cosine similarity. And this is like teaching a machine to understand the word visually and verbally at the same time. And you're now equipped to build models that process both data at the same time. And then we brought it all together with our multimodal RAG. We built it, you learn how to fine-tune it, use prompts, even combine different outputs. And therefore, you are no longer a learner nor a spectator. You can build systems, and you can build RAG systems that are very cool and are very, very good. Therefore, big picture, you're ready for this. you have accomplished a lot, and therefore you're now ready for more. Until next video, have fun. Welcome back. Before we actually start tokenizing with Python, let me show you a tool built by OpenAI. This tokenizer can come to this link, so platform.openai.com/tokenizer. This should also be something that you don't need to pay, but let me actually triple check. Now I have it top of mind, so I go to this incognito, and okay, here it is. Let me just text something. Hey, show example. Oopsie, not this. So, hey, and here we go. We see here. So this works. I don't really like all this black, so we go here. And the way that it works is that I want to show you how tokenization here is actually working. So for instance, I would write here some text. Hey, I would like to see some examples of tokenization. The question is, how is actually OpenAI tokenization? How is actually OpenAI tokenizing all of this? So if you come here, this is how it's actually working. So we have, hey, this is one token, the comma, another token. Then we have the hi, the I, but have in mind that the token here also includes the space. So it's space and the I, this is also a token. And then I would like to see some examples of tokenization. And here in the tokenization, you can definitely see that not always is one token, one word. It can happen that one word is split because we have token, which means something, and then we would have ization, which adds meaning to the word token. But at the same time, the main thing is token. Now, this is how it's actually working, but then what we have are also token IDs. And these are mathematical representations of our tokens. And what we should see is stuff that is pretty spread apart, if it makes sense or not. Now, let me show it to you. So we would have, I like apples, apple pie, and Apple iPhone. So everything connected to apples. And let me actually add a comma here. According to Grammarly, I should use. Let me add the dot. Let's have a look here at examples. And we can see here, so I like apples, comma, apple pie, comma, and Apple iPhone. See how the iPhone is actually with two different tokens. And as well see here that Apple with capital A or uppercase versus Apple with lowercase. These are different tokens. And then we have here apples, plural, also different token. And then we see here, so I like apples, comma, apple pie, and then Apple iPhone. And if we see here, so apples, apple, and apple, like they are also very spread apart. The way that this works is that if the numbers are close together, they have somewhat of a similar meaning. So for instance, we would always most likely see that the commas, which are represented under the name or under the number 11 here, they are close together as well. Dot 13 close together. But then we have Apple iPhone, and then we would see that, for instance, the Apple capital A and then phone, this is somewhat close together. But then we would then see the apples that is very far away from, Apple or even the apple pie. Now, of course, this is just a tiny amount of tokens. We could definitely play around with much bigger text, but this is how this is all getting connected with the tokens. And as we go and explore throughout this section and throughout this course, we will learn about this tokenization further, about other stuff which is called embeddings. There's like a lot of stuff that we need to learn. But you can definitely see here. And at the same time, you can try to see these other models, which they differ here. So if you, depending on which model you're using, the tokenization is also a different process. And as well, so tokens 12 and 43. And if you go to 3.5 and 4, we just have 11 tokens. So you see here that, for instance, it was actually the iPhone that got, merged together. At the same time, one cool thing here, or one important thing to know, is that one token is on average 4 characters. And this means that 100 tokens is 75 words. Now, this is actually no longer a thing, but 1 or 2 years ago, token limit was relevant, not anymore. So as I was doing the RAG course assistant for you, there are around 80,000 words while I speak through this course. And therefore, that's 60,000 tokens. Currently, not an issue because some models have more than 100K, or almost all models have more than 100K tokens. So that's definitely not the issue anymore. But have in mind that as I build, maybe I'll even actually reach this limit. That is it. So I hope you see that how this tokenization is happening. Key things to highlight. The token will be different if our word is all caps, if it has a uppercase, a lowercase, because all of this has different meanings. Tokens that most likely are somewhat similar, they'll probably merged or have a number that is similar to each other. Of course, this is not a hard rule, but that is the case, right? And words that are very much, far apart in terms of their meaning, also their mathematical representation under these token IDs, they will also be far apart. This is it. Till next video. Have fun. And that's a wrap. That's how you supercharge an AI with Retrieval Augmented Generation. No more random hallucinations, just relevant, data-driven answers. If you're hungry for more, the full RAG course has you covered. We go beyond these core lessons into multimodal RAG, unstructured data, and knowledge graphs with light RAG. So your AI can reason about visuals, audio, and complex domains alike. And we don't stop there. We explore agentic RAG for truly autonomous problem solving and wrap it all up with capstone projects that get you building real-world solutions. If you haven't already, download the rest of the materials and dive deeper into the modules on OpenAI integration, advanced prompt engineering, and more. Because in this course, we're not just learning about AI, we're building the AI of tomorrow. Thank you for watching, and I'll see you in the next video.